Imagine that you're standing on the edge of a boundless ocean, with a sparkling cosmos reflected in its waters. Now imagine that this panorama with its myriad stars and spinning galaxies is just a reflection, a projection from an invisible, distant shore. This is not the beginning of a science fiction tale, but a look at one of the most striking theories in modern physics: the holographic principle. Just as each droplet on a spider's web contains the world in miniature, our universe may be a grand reflection of fundamental laws written on a distant frontier. Far from the solid earth beneath our feet and the emptiness of space, the very fabric of our reality may be generated by something much deeper, something beyond our present comprehension. Let's go on this exploration together and try to answer the ultimate question: does the fabric of our universe arise from a holographic boundary? At the heart of physics is a quest to uncover the layers of reality to reveal its most fundamental elements. These elements, known as ontological primitives, are the foundation upon which the vast edifice of the universe is built. For centuries, physicists have searched for these building blocks, seeking to understand the rules governing their interactions. The journey begins with the concept of space. Isaac Newton, one of the titans of science, envisioned space as an absolute, unchanging background, indifferent to the comings and goings of matter and energy. For Newton, space was an absolute receptacle, an infinite space in which all the events of the universe were played out. However, as our understanding deepened, this view of space began to evolve. The advent of Einstein's theory of relativity painted a different picture, in which space was not just a passive arena, but an active participant in cosmic interaction. According to the new view, space could bend and curve in the presence of mass and energy, calling into question the very notion of its absoluteness. Amid the shifting perspectives, a radical idea emerges: the holographic principle. This principle suggests that our three-dimensional perception of the universe may be akin to a hologram, a projection from a two-dimensional surface located at the edge of space. This edge, though infinitely distant and inaccessible to direct observation, may contain the fundamental information that gives rise to everything we perceive as reality. This concept overturns our usual notions by arguing that the very essence of space, the fabric of our reality, may not be a fundamental characteristic of the universe, but is emergent. Emergentism describes phenomena that arise from the complex interaction of simpler elements, leading to new properties and behaviors that are not obviously based on the components alone. In the context of our universe, and especially within the holographic principle, emergentism takes on a fascinating role. Here, the term implies that the three-dimensional space we move through and the time we experience are not the fundamental building blocks of reality. Instead, they arise from a more basic two-dimensional structure, the holographic boundary that encodes the information and laws that give rise to our perceived reality. In this framework, every star, planet, and galaxy, every law of physics, from gravity to electromagnetism, and the very fabric of the cosmos, are emergent phenomena. It's something like a bridge between the known and the unknown, between the observable dimensions of our universe and the fundamental coding of reality at the holographic boundary. It invites us to rethink not only the structure of the cosmos, but the very nature of reality as we peel back the layers of the universe. Against the backdrop of our hypothesis, black holes, where gravity triumphs to such an extent that even light can't escape it, have become those unexpected heroes, thanks to the pioneering insights of Stephen Hawking and Jacob Bekenstein. Hawking and Bekenstein ventured into uncharted territory by attempting to combine the fields of quantum mechanics and general relativity theory in order to explore the thermodynamics of black holes. Their theories reveal the startling fact that black holes are not absolute endpoints of entropy, but rather key players in the cosmic interaction of information and energy. Entropy, traditionally associated with disorder in a system, took on a new dimension in their hands. It became a veil hiding information inside black holes. It wasn't just about the randomness or disorder of particles, but about the hidden layers of information that define the very structure of reality. As matter spirals into a black hole, it seems to disappear from our universe, which raises a major question. What happens to the information it carries? This question calls attention to entropy, not just as a measure of disorder, but as a key to understanding the fate of ingested information. The entropy of a black hole, as proposed by Bekenstein, is directly proportional to its surface area, not its volume, a concept that contradicts our everyday understanding of physical laws. This relationship between surface area and entropy leads us to a profound conclusion. The maximum amount of information that can be contained in any given region of space is determined not by its volume, as one might intuitively assume, but by its surface area. This view laid the foundation for the holographic principle, which assumes that all the information of a volume can, in principle, be encoded on a two-dimensional surface. Thus, Hawking and Bekenstein's discoveries of black hole thermodynamics suggest a cosmos in which the very fabric of reality, every particle, every force, and the very dimensions of space and time can only be emergent properties emerging from a deeper two-dimensional fabric. At the forefront of bridging the gap between the mysteries of black hole thermodynamics and the holographic principle is Juan Maldacena's ADS-CFT correspondence. This work is not just a framework, but a concrete example of holographic principles in action. Maldacena's correspondence asserts a duality between a type of space known as anti-de Sitter space, abbreviated ADS, and conformal field theory, or CFT, which exists at the boundary of this space. Despite the positive cosmological constant of our universe, which contrasts with the negative constant of ADS space, the principles derived from this duality provide insight into the nature of gravity and quantum mechanics, and, by extension, the holographic nature of our universe. Central to this dualism is conformal field theory, which operates on the boundaries of the universe within the ADS-CFT framework. CFT is unique in its scale invariance. The laws governing these field theories remain unchanged, regardless of the size or scale at which they're observed. This property of CFT is key because it encodes the information needed to describe higher dimensional bulk space within a lower dimensional framework, effectively illustrating the holographic principle. Scale invariance within CFT is not just a mathematical curio, it's a window into the emergence of dimensions and the very fabric of space itself. Different scales of patterns at the boundary, governed by the uniform laws of CFT, contribute to the illusion of three-dimensional space. This phenomena emphasizes the holographic principle that the complexity and dimensions of volume space arise from simpler scale-variant dynamics at the boundary. Through the prism of ADS-CFT and the intricacies of conformal field theory, we gain a deeper understanding of how the dimensions and the very structure of space-time can emerge. scale-invariant boundary patterns, each contributing to the holographic encoding of the universe. One of the most obvious metaphors for this complex idea is the concept of nested spheres. These nested spheres serve as a visual framework, with each layer representing different scales of boundary patterns. The finest patterns, akin to the microscopic level, are densely packed with information and require high-resolution understanding. As you move to finer spheres, the patterns become coarser, encapsulating the same information, but in a more generalized, less detailed form. In the microscopic space of the holographic boundary, the patterns are dense and highly detailed, resembling the fine strokes of a master painter. These fine-grained patterns are the most fundamental level of the universe, where every tiny element is filled with information encoding the laws of physics and initial conditions of cosmic phenomena. Moving from the micro to the macro environment resembles looking at a mosaic. Up close, we see only individual tiles, each with its own color and shape, but at a distance, a complex and holistic image emerges. Similarly, the grand structure of the universe, galaxies, stars, and planets, emerges from the collective behavior of fundamental patterns encoded on the holographic boundary. This transition from fine to coarse-grained patterns at the boundary of the universe is not just a feature of the holographic model. It's a fundamental process that shapes our perception of space. It emphasizes the difference in information requirements at different scales, demonstrating the adaptability and efficiency of the holographic encoding of space. This concept of a holographic universe is based on a profound philosophical and scientific notion: ontological democracy. This idea suggests that the boundaries of the universe, with its two-dimensional encoding of information and the three-dimensional space we're all familiar with, can be equally fundamental to the fabric of reality. Neither is more real or primary than the other. Rather, they coexist in a state of mutual emergence. This view has far-reaching implications. It suggests that what we perceive as the three-dimensional reality of stars, galaxies, and planets, with all their complex interactions, may be a manifestation of deeper, more fundamental laws encoded at a distant, invisible boundary. This coding not only dictates the structure of the volume, but is also shaped by events within it, creating a feedback loop. In our journey through the holographic universe, we encounter a profound rethinking of gravity, which is traditionally viewed as the curvature of space-time under the action of mass. In the holographic framework, gravity arises not from mass itself, but from entropic forces acting on the information encoded at the boundary of the universe. The idea that gravity might be an emergent phenomenon, like temperature or pressure in thermodynamics, represents a radical shift in perspective. It suggests that what we perceive as gravitational attraction is the result of the universe's tendency to maximize entropy, an idea first proposed by physicist Eric Verlinde. This theory suggests that gravitational attraction arises from changes in the amount of information associated with the position of material bodies. The holographic universe also pushes us to explore the mysterious role of quantum entanglement in the fabric of space-time. Quantum entanglement, the phenomena in which particles remain bound in such a way that the state of one particle can instantaneously affect the state of another, regardless of the distance separating them, may be the thread that weaves the spatial continuum of the universe. According to this view, space itself arises from the entanglement of quantum bits encoded at the cosmic boundary. When particles are entangled, they share a common bond that contributes to the illusion of continuous space. Theoretically, unraveling these particles could lead to the disappearance of the space between them. which calls into question the very notion of distance and locality in our universe. The principle of a holographic universe, of course, like many other theories in physics, poses one ultimate question, the question of finding a universal holographic model. This ambitious endeavor is designed to reconcile the myriad complexities of the universe into a single structure that accurately describes both the immense cosmic scale and the minutiae of quantum mechanics. The challenges in this endeavor are enormous. Creating a universal model requires not only a deep understanding of quantum mechanics and the general theory of relativity, but also a new approach to integrating these theories into a holographic framework. Potential breakthroughs promise to revolutionize our understanding of the cosmos. A successful, universal holographic model could provide unprecedented insights into the origin of the universe, the nature of black holes, and the fundamental laws governing reality. As we journey through the possibilities of the limits of this theory, we may be on the threshold of a new understanding of the cosmos, or another refutation of a high-profile theory. If reality is holographic, then our perception, experience, and very existence may be far more intertwined with the cosmos than we ever imagined. This journey is fraught with challenges and unknowns, but the promise of unlocking the deepest secrets of the universe propels us forward in pursuit of an elusive universal model that will redefine our place in the cosmos. In the field of space exploration, the James Webb Space Telescope is a beacon of human ingenuity and curiosity. Its recent incursion into the depths of our solar system has revealed discoveries that challenge the possibility of life beyond Earth. Among the many celestial bodies orbiting our giant neighbor Jupiter, Europa is a world of special interest. With its jagged surface and hidden ocean, this icy moon has long intrigued scientists and dreamers alike. However, it's the recent discovery of JWST that's brought Europa into the spotlight of astrobiological research. JWST, in an unprecedented observation of the moon, has discovered carbon dioxide on Europa's surface. This discovery, while seemingly simple, has profound implications. Carbon dioxide, a molecule integral to life as we know it here on Earth, could be a marker pointing to the potential for life on extraterrestrial worlds. Let us together delve into the data obtained by JWST. What secrets does Europa hide beneath its icy facade? Could the discovery of carbon dioxide be a clue to life beyond Earth? Europa, a moon full of mystery, is a landscape both alien and fascinating. Its surface is covered in a canvas of ice with a complex network of lines and ridges. These features, known as lineae, are not just surface scars, but tell the story of the dynamic geologic processes taking place. This 9 to 15-mile thick ice shell hides a vast ocean that has interested scientists for decades. The lines on Europa's surface are believed to be the result of the ice crust interacting with the moon's underground ocean. These cracks and ridges form as the ice shifts and breaks, a process driven by Europa's motion around Jupiter. Beneath this frozen barrier is a salty ocean, estimated to be 40 to 90 miles deep. This hidden sea, dark and cold, is kept liquid not by solar heat, but by Jupiter's immense gravitational pull. So-called tidal deformations. The satellite rotates around its giant parent and generates enough heat to maintain the ocean's liquid state. The chemical composition of this ocean is the subject of intense research and speculation. It's believed that there may be hydrothermal vents on the ocean floor, similar to those found in Earth's oceans. These vents may provide the necessary energy and minerals to sustain life, making Europa's oceans a prime candidate for the search for extraterrestrial life. The physical properties of Europa's oceans also raise intriguing questions. The presence of salts and the ability to form complex organic compounds, combined with the energy of hydrothermal activity, create an environment in which life can exist. Ocean depths and pressures, although extreme, are not beyond habitability, as evidenced by life in the deep gorges on Earth. Europa's mysterious environment with its icy surface and ocean is an interesting case for research. But what exactly has attracted the eyes of scientists to this moon this time? With the help of JWST, astronomers have made an interesting discovery. Using data from NASA's Space Telescope, they've detected carbon dioxide on the icy surface of the satellite. This discovery is not just an addition to Europa's chemical profile, it's an important key to understanding the moon's potential for life. Using the near-spec near-infrared spectrograph, JWST has discovered carbon dioxide in the geologically young and chaotic Terra Regio locality. This discovery is not just about the presence of a molecule, it's about its origin. The carbon dioxide on the surface of Europa is thought to have come from within, from its mysterious underground ocean, rather than having been deposited by external forces, such as meteorites. This discovery suggests a dynamic exchange between Europa's ocean and its icy shell. The most interesting thing here is that carbon dioxide is unstable on Europa's surface, suggesting constant replenishment from the moon's interior. The presence of carbon dioxide in the young terrain region indicates a recent and possibly ongoing process. This exchange may hold the key to understanding ocean chemistry and, by extension, its ability to support life. This discovery was made possible by the near-spec JWST instrument, which provided detailed spectra of Europa's surface. The ability to pinpoint the location of specific chemicals, such as carbon dioxide, allows astronomers to build a more complete picture of Europa's chemical landscape. Each discovery adds a piece to the puzzle of this mysterious moon. But why is this gas being released? And even more so, how does this cosmic body remain warm, supporting a liquid subsurface ocean? Europa, in its gravitational interaction with Jupiter, experiences a phenomenon known as tidal deformation, or tidal flexing. This process, caused by Jupiter's enormous gravitational pull, is one of the key factors in shaping Europa's potential to harbor life. As Europa revolves around Jupiter, its shape is constantly bending. This constant bending generates significant internal heat, a process quite different from the solar heating that we're familiar with on Earth. This internal heating is critical because it's thought to keep Europa's underground ocean in a liquid state, despite the relatively low temperature of outer space. The heat generated by tidal bends may also stimulate geologic activity on Europa, such as subglacial volcanism and hydrothermal vents. These openings, if present, may be similar to those in Earth's deep oceans, which teem with life despite the lack of sunlight. The energy provided by tidal bends could be a crucial ingredient for life. In Earth's oceans, hydrothermal vents support entire ecosystems where life forms utilize chemical energy released from the Earth's interior. On Europa, a similar process could occur, with life forms potentially using the energy from hydrothermal vents to power their metabolic processes. In such an environment, life could exist independently of sunlight, relying instead on the chemical and thermal energy provided by Europa's internal dynamics. Carbon dioxide, a molecule so integral to life on Earth, now takes center stage in the discussion of extraterrestrial life. On our home planet, carbon dioxide is the cornerstone of the biological process of photosynthesis that drives Earth's ecosystems. But what role can this essential molecule play in the cold, alien environment of Europa? The discovery of carbon dioxide on Europa by the James Webb Space Telescope opens up intriguing possibilities. In extraterrestrial environments, especially on icy moons like Europa, carbon dioxide may play a different but equally important role in sustaining life. In the absence of sunlight, life in Europa's oceans will have to rely on chemical energy, a concept known as chemosynthesis. This is where carbon dioxide can play a key role. In Earth's deep oceans, some organisms use carbon dioxide combined with hydrogen from hydrothermal vents to create organic matter. This process, although independent of sunlight, is a fundamental aspect of life in extreme environments. The presence of carbon dioxide on Europa may indicate a similar process. If there are hydrothermal vents in Europa's oceans, as many scientists believe, these may be the very places where life forms use carbon dioxide, perhaps like Earth's deep-sea organisms. This leads to an intriguing question. Could the carbon dioxide on Europa's surface be a byproduct of biological activity in its oceans? While the topic remains speculative, such a possibility adds an exciting dimension to the search for life beyond Earth. The role of carbon dioxide in extraterrestrial biological processes is the subject of intense research and speculation. Its presence on an icy moon may be a marker indicating the potential for life in environments far removed from the sunlit world we know. So let's summarize. The key to Europa's potential habitability lies in three basic elements: liquid water, an energy source, and the necessary chemical elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Europa's subsurface ocean and the energy generated by tidal bends are consistent with the first 2 points, and the presence of carbon dioxide on its surface hints at the presence of the necessary elements. Detecting carbon dioxide on Europa is an important piece of the puzzle. On Earth, carbon dioxide is integral to life, playing a central role in photosynthesis and respiration. In the alien environment of Europa, this molecule may be equally important, potentially acting as a building block or part of metabolic processes for hypothetical life forms. The presence of carbon dioxide also suggests that Europa's environment is chemically active, a key factor in the search for life. This activity could indicate geologic processes or even hint at biological processes if life existed there. It's also only possible to emphasize the importance of studying Europa's ocean as a testing ground for understanding the origin of life. The conditions on Europa may be similar to those of early Earth, giving a rough idea of how life could have originated under extreme conditions. On Earth, carbon dioxide is a fundamental component of life, involved in processes such as photosynthesis and respiration. In the alien environment of Europa, this molecule could play a similar role, potentially serving as a building block for life or part of the metabolic processes of a life form. Carbon dioxide could be a byproduct of biological activity or a resource. As we stand on the threshold of a new era in astrobiology, the significance of the discoveries of the James Webb Space Telescope propels us into a future rich with possibilities. Upcoming missions to Europa, particularly the European Space Agency's JUICE, Jupiter Icy Moons Explorer, and NASA's Europa Clipper, are designed to broaden our horizons and deepen our understanding of this enigmatic moon. NASA's JUICE mission, launched on April 14, 2023, aims to make detailed observations of Jupiter and its 3 large icy satellites, with a particular focus on Ganymede. However, the Europa survey will provide important data that will complement JWST's findings by providing insight into Europa's icy crust and its subsurface ocean. In turn, NASA's Europa Clipper, scheduled for launch in October 2024, is designed specifically to study Europa. Equipped with a suite of sophisticated instruments, this mission will conduct a detailed reconnaissance of Europa's ice shell and subsurface ocean in search of signs of habitability. The purpose of these missions is to build on JWST's groundbreaking discoveries, delve into the mysteries of Europa's environment. By scrutinizing Europa's surface, analyzing its ocean, and searching for biochemical signatures, these missions will improve our understanding of this moon's potential to support life. By the way, you still have a unique opportunity to be part of this historic exploration and get into the history of this remarkable moon. To quote NASA, join the mission and have your name engraved on NASA's Europa Clipper spacecraft as it travels 1.8 billion miles to explore Europa, an ocean world that may support life. Sign your name today to the message in a bottle. End of quote. Just imagine at a time when some people haven't even visited the next country, a piece of your personal history will travel such distances to orbit another planet. A truly mesmerizing thought. By adding your name, you're not just leaving a personal mark, you're becoming part of a legacy that will resonate in the annals of space exploration. Europa, once a distant and icy moon, is now the center of our quest to understand the existence of life beyond Earth. The JWST results, combined with future JUICE and Europa Clipper studies, usher in a new era of astrobiology. An era in which the search for extraterrestrial life is moving from the realm of speculation to reality. For centuries, we've gazed into the night sky, listening to the stories told by the light of the distant stars. We've built telescopes to see deeper and farther, to uncover the secrets hidden within the cosmos. But light is only part of the story. There is another, more subtle language that the universe speaks. A language of ripples and echoes, written into the very fabric of space and time. Welcome to the era of gravitational wave astronomy. Gravitational waves are ripples in the fabric of space-time, predicted over a century ago by Albert Einstein. Unlike electromagnetic waves, such as light, radio, or X-rays, which are vibrations of electric and magnetic fields, gravitational waves are distortions in the very structure of space and time itself. They're created by some of the most violent and energetic events in the universe. Einstein's general theory of relativity, published in 1915, proposed that massive objects like stars and planets don't simply exist in space, they warp and curve it. This distortion is what we perceive as gravity. But Einstein went further. He suggested that when these massive objects accelerate, when they move, collide, or explode, they create ripples in space-time. Much like a stone thrown into a pond creates ripples on the water surface. Gravitational waves are produced by cataclysmic events, collisions of black holes, explosions of supernovae, the merging of neutron stars. These waves travel across the universe at the speed of light, carrying with them information about the events that created them. They tell us about the nature of gravity, the properties of black holes, and the birth of stars. But gravitational waves are incredibly weak by the time they reach us. Having traveled billions of light years across space, detecting them requires instruments of unprecedented sensitivity, machines capable of measuring changes of distance smaller than a fraction of the width of a proton. This is the challenge that scientists have faced for decades. In the 1990s, a new generation of scientists set out to build such an instrument. The result was LIGO, the Laser Interferometer Gravitational Wave Observatory. It consists of two massive detectors, one in Washington and the other in Louisiana, that are designed to detect these faint ripples in space-time. Their construction marked the beginning of a new era in the search for gravitational waves. Gravitational waves don't just pass through the vast reaches of space, they also pass through us. As these waves travel across the universe, they stretch and squeeze the space they move through, causing distances between objects to change. But the question arises, do gravitational waves stretch us too? In theory, yes. Gravitational waves do stretch and compress everything in their path, including us. However, the effect is incredibly tiny. A passing gravitational wave would stretch you by less than the width of an atomic nucleus. It's so small that it can't be felt or noticed by us in any way. At LIGO, the world's most precise measuring device, a laser interferometer is used to detect these minuscule changes. The device splits a laser beam and sends the two halves down perpendicular arms, each several kilometers long. When a gravitational wave passes by, it changes the length of these arms by a tiny amount, altering the interference patterns of the light. This change indicates that a gravitational wave has passed. Thus, while gravitational waves do indeed stretch us, their effects are so minute that they can only be detected by the most advanced technology, like the instruments at LIGO. Through these ultra-precise measurements, we're able to hear the faint whispers of the universe. Gravitational waves are not just distortions in space-time. They also carry energy. When massive objects like black holes merge, they release an enormous amount of energy in the form of gravitational waves. This energy travels across the cosmos, rippling through space-time and revealing the most powerful events in the universe. The first detection by LIGO in 2015 confirmed that these waves carry energy away from their source, causing the black holes to spiral towards each other and eventually merge. The amount of energy carried by these waves is staggering. In just a fraction of a second, the merging black holes emitted more energy than all the stars in the observable universe combined. This discovery not only confirmed Einstein's theory, but also opened a new way to understand the most energetic processes in the universe, revealing information about the objects and events that created these waves. Each detection tells a story of the formation and evolution of black holes, neutron stars, and even entire galaxies. The energy carried by gravitational waves does more than just stretch space. It allows us to map the universe's most extreme environments, to understand how black holes and neutron stars form, and to explore the very nature of space and time. Gravitational waves not only affect the space they move through, they also have profound effects on the very objects that create them. When two massive objects like black holes merge, the gravitational waves they emit carry away significant amounts of energy. This loss of energy directly impacts the motion and structure of the black holes themselves. When neutron stars collide, the effects are even more dramatic. Gravitational waves not only strip away energy, but also determine the final outcome of the collision. Whether a new, more massive neutron star is formed, or whether the stars collapse into a black hole. These waves provide clues about the internal structure and composition of these dense, enigmatic objects. The gravitational waves we detect are signals from the heart of cosmic violence, revealing the forces at play, the incredible energies involved, and the final fate of these cosmic giants. They help us understand how stars live and die, how black holes are born, and how matter behaves in the most extreme environments imaginable. To detect gravitational waves, scientists needed to build an instrument unlike any other: the Laser Interferometer Gravitational Wave Observatory, or LIGO. Its design is based on a simple but powerful idea: using light to measure the tiniest distortions in space. The principle behind LIGO is simple in concept, but complex in execution. A powerful laser beam is split into two, sending the light down two long arms, each 4 kilometers in length. At the end of each arm, mirrors reflect the light back to the central beam splitter, where the two beams are recombined. In the absence of a gravitational wave, the beams cancel each other out perfectly due to their carefully calibrated paths. However, when a gravitational wave passes through Earth, it stretches space in one direction while compressing it in the perpendicular direction. This changes the length of the arms, altering the time it takes for the laser beams to return, creating a distinctive interference pattern that LIGO's detectors can measure. To detect these incredibly small changes, LIGO must operate under extreme conditions. The entire interferometer is housed in ultra-high vacuum tubes to eliminate air molecules that could scatter the laser light. The mirrors are suspended by finely tuned systems that isolate them from ground vibrations caused by traffic, wind, or distant earthquakes. LIGO is not alone in its quest to detect gravitational waves. Across the globe, a network of observatories works together to listen to the universe, combining their data to improve the precision and reliability of detections. Virgo, located near Pisa, Italy, is LIGO's European counterpart. With its 3-kilometer-long arms, Virgo uses the same principles of laser interferometry to detect gravitational waves. By collaborating with LIGO, Virgo helps pinpoint the location of cosmic events, allowing astronomers to direct their telescopes to the right portion of the sky at the right time. In Japan, the Kagra Observatory brings new innovations to the field. Located deep underground to shield it from surface noise, Kagra also uses cryogenically cooled mirrors to reduce thermal vibrations, making it even more sensitive to gravitational waves. By combining data from detectors on different continents, we can determine the location of gravitational wave sources with much greater accuracy. When a gravitational wave passes through Earth, it arrives at each observatory at slightly different times. By measuring these time differences, we can pinpoint the source of the waves in the sky. This global network has enabled us to conduct multi-messenger astronomy, where gravitational waves are observed alongside light, radio waves, and gamma rays. Together, they paint a fuller picture of the most extreme cosmic events. Gravitational wave astronomy is truly a global effort. Scientists from every corner of the world are working together to unlock the universe's secrets, proving that in science, collaboration knows no borders. Gravitational waves come in a wide range of frequencies, and each frequency reveals a different story about the universe. LIGO and its partner observatories are tuned to capture specific frequencies that align with some of the most energetic events in the cosmos. LIGO is designed to detect gravitational waves in the frequency range of approximately 10 Hz to 10,000 Hz. This range is well suited for capturing waves produced by events like the merging of stellar mass black holes or the collisions of neutron stars. These frequencies fall within a range similar to that of human hearing, but instead of sound waves traveling through air, they are ripples traveling through space-time. Each gravitational wave signal can tell us about the objects that created it. For example, a merger of two black holes produces a chirp, a wave pattern that increases in frequency and amplitude as the black holes spiral closer together, culminating in a sudden peak as they merge. The unique signature of each chirp allows scientists to determine the masses, spins, and distances of the merging objects. However, not all gravitational waves fall within LIGO's detection range. Lower frequency waves, such as those produced by the mergers of supermassive black holes found in the centers of galaxies, lie outside LIGO's current capabilities. Detecting these lower frequency waves requires different types of instruments. And this is where the future of gravitational wave astronomy comes into play. The planned Laser Interferometer Space Antenna, or LISA, will be positioned in space to detect these lower frequency gravitational waves. By expanding our observational range, LISA will allow us to hear the deep, slow rumblings of supermassive black hole mergers and other cosmic phenomena to further extend our understanding of the universe. By broadening the range of detectable frequencies, we'll open up new windows into the universe, enabling discoveries from high-pitched chirps of merging neutron stars to the low-frequency growls of supermassive black holes colliding. Each new frequency band brings with it new opportunities for understanding the cosmos. In August 2017, a groundbreaking moment in astronomy took place. For the first time in history, an astronomical event was observed in both gravitational waves and electromagnetic radiation. This event, known as GW 170-817, marked the dawn of multi-messenger astronomy. GW 170-817 was the merger of two neutron stars, the remnants of massive stars that had previously exploded as supernovae. As these neutron stars spiraled together, they emitted gravitational waves detected by LIGO and Virgo. Just 1.7 seconds later, NASA's Fermi Gamma Ray Space Telescope observed a burst of gamma rays, pinpointing the event's location in the sky. This unique observation triggered an unprecedented global effort. Within hours, dozens of telescopes across the planet began observing the region in different wavelengths, from radio to X-rays, allowing scientists to study the event in detail like never before. This first-ever joint observation provided critical insights into the universe's workings. It confirmed that neutron star mergers are key sites for producing heavy elements, such as gold and platinum, and scattering them throughout the cosmos. This was a long-suspected theory, now proven with direct evidence from gravitational waves. The discovery of GW 170-817 demonstrated the immense power of combining gravitational wave and electromagnetic observations, allowing us to witness cosmic events with greater clarity and precision. It opened a new window into the universe, where every detection tells a deeper, richer story. Multi-messenger astronomy represents a new era of discovery, where light and gravitational waves together illuminate some of the most profound mysteries of the cosmos. Gravitational wave astronomy is still in its infancy, but its potential is vast. What could we uncover in the coming years and decades? What new mysteries of the cosmos might we solve? With more sensitive detectors and more powerful instruments, we might soon detect gravitational waves from sources we've never observed before. Could we hear the faint echoes of the Big Bang, confirming theories about the earliest moments of the universe? Detecting these primordial waves could provide direct evidence of cosmic inflation, the rapid expansion of the universe just moments after the Big Bang. It could answer questions about the fundamental forces that shape the cosmos. Gravitational wave astronomy could also reveal unknown phenomena, objects or events that we've never imagined, exotic forms of matter, hidden dimensions, or the mysterious dark matter that makes up most of the universe's mass. Gravitational waves could help uncover these elusive secrets. We're standing at the edge of discovery, poised to answer some of the most profound questions ever asked about our universe. Gravitational wave astronomy offers a new way to explore the cosmos, opening a path to discoveries beyond our wildest dreams. The universe is full of whispers, and we are just beginning to listen. In the serene silence of space lurks a discovery that raises a million questions. Imagine a region of space where the rules seem to have been rewritten, where a celestial anomaly hints at the existence of a cosmic giant, a black hole known as Gaia BH3. Black holes have long attracted the curiosity of scientists and everyday people alike. These mysterious objects of the universe exert such a strong gravitational pull that even light cannot escape their grip. By anchoring themselves in the fabric of space-time, they affect the environment in a subtle yet profound way. But how would such a discovery affect us, only 2,000 light-years away? Could this silent neighbor have any impact on our solar system? Or does its presence only expand the cosmic mysteries that surround us? So we all know that deep in the universe, black holes exert a gravitational pull so strong they bend the very fabric of space-time. These cosmic mysteries are not just points in space, but dynamic regions where gravity is so strong that the ordinary laws of physics have trouble holding it together. But let's understand the nature of these celestial phenomena in more detail. The gravitational force of a black hole is indeed powerful. It's what causes space-time to warp and light to be delayed. But its influence, however powerful, is constrained by the vastness of space. The idea that a black hole can simply roam the cosmos, devouring stars and galaxies, is a misconception often propagated not by science but by sensationalism and movies. The reality is that the gravitational influence of black holes does not extend indefinitely. On the contrary, their influence decreases sharply with distance. So even black holes relatively close to our solar system, such as Gaia BH3, don't pose an immediate threat. To make sense of this, we turn once again to history. More specifically, the story of Cygnus X1, the first black hole to be discovered and confirmed. The story begins with not just a discovery, but with a daring wager in the world of astrophysics. It was the late 1960s, an era of celestial exploration and fierce debate among scientists. Cygnus X1 was first detected as an unusually strong X-ray source by a sounding rocket launched in 1964. This source was not just another point of light in the night sky, but a source emitting X-rays with an intensity that outshone almost everything else in the celestial sphere. The intrigue escalated when two of the most brilliant minds of the time, Stephen Hawking and Kip Thorne, made their now famous bet. Thorne bet that Cygnus X1 was a black hole, and Hawking bet against it, hoping to be proven wrong as part of his deep quest to understand these cosmic phenomena. This wager symbolized the scientific curiosity and somewhat playful rivalry that drive many scientific discoveries. Cygnus X1 is part of an X-ray binary system consisting of a blue supergiant star and what is believed to be a stellar mass black hole. The intense gravitational pull of the black hole pulls material away from its stellar companion, which spirals into the black hole, heating up to millions of degrees and emitting X-rays. These emissions have allowed astronomers using instruments such as the Uhura satellite launched in 1970. The first satellite, by the way, specifically designed to study X-ray sources, to study the properties of this mysterious object more closely. The Uhura satellite, being the first space telescope, has provided convincing evidence that this object is indeed a black hole. Moreover, the first of its kind. Cygnus X1 has taught us much about the nature and behavior of black holes, particularly how they interact with nearby matter. It serves as a crucial point of reference in the study of Gaia BH3. Despite the large mass of Gaia BH3 had a whopping 33 solar masses, it remains a silent observer in space. primarily because of its considerable distance from a star capable of providing material for an accretion disk. This distance suggests a lack of appreciable X-ray emission and a quiet existence, in stark contrast to the dynamic environment around Cygnus X1. While Cygnus X1 is about 7,000 light-years away from Earth, Gaia BH3 is closer, at a distance of about 2,000 light-years. Despite this proximity, Gaia BH3's passive nature and our advanced understanding of black hole mechanics give us confidence in its safety. Through the lens of the history and advances in the study of black holes, we see that these amazing objects, while powerful, are constrained by the laws of physics, making the fear of them as interstellar predators unfounded. So in the relentless quest to understand our universe, the Gaia telescope has become a key player in the latest chapter of space exploration. Designed to map stars with unprecedented accuracy, it has brought a new player into the cosmic arena. The massive black hole Gaia BH3, now the closest black hole to us. A mission to map more than 1 billion stars has given us a clearer picture of our galactic neighborhood than ever before. It was during this careful survey that the telescope discovered an anomaly. A star whose motion could not be explained by ordinary celestial mechanics alone. This star, seemingly invisible, indicated the presence of something massive, hidden from view. And who is the culprit? Why, Gaia BH3, a previously unseen black hole, hiding in the galactic halo about 2,000 light-years away. Gaia BH3 is not just a black hole. It's a colossus of the cosmos, with a massive 33 solar masses. This discovery places it among the heaviest stellar mass black holes found in our galaxy. Its location in the galactic halo, a region populated by older stars and globular clusters, adds to its intrigue by suggesting a different origin or evolution from black holes found in the galactic disk. One of the most mesmerizing aspects of Gaia BH3 is its silence. Unlike infamous black holes that make their presence known by devouring nearby matter and spewing X-rays, Gaia BH3 remains eerily quiet. The key to the silence lies in its isolation. The black hole's companion star orbits at a safe distance, too far away to be torn apart and fall into the typical perdition spiral that forms an accretion disk. This distance prevents any significant material transfer, and as a result, Gaia BH3 lacks the usual signs of black hole activity, such as the powerful jets and strong X-ray emission seen in systems like Cygnus X1. The recent discovery of Gaia BH3 not only expands our catalog of known black holes, but also sheds light on the mysterious process of black hole formation from metal-poor stars. Metal-poor stars, composed mostly of hydrogen and helium with scant traces of heavier elements, represent an early generation in the stellar history of the universe. These stars, due to their minimal metal content, lack the materials necessary for heavy element synthesis processes, which significantly affect their life cycle and demise. The star orbiting Gaia BH3 has been identified as metal-poor, which is a crucial clue to understanding its evolutionary path and the nature of its colossal companion black hole. Typically, the fate of a massive star involves a supernova explosion heralding the death of the star and the birth of a neutron star or black hole. For metal-poor stars, however, the scenario can be significantly different. The reduced opacity due to the lack of heavy elements allows the stars to retain most of its mass, leading to a higher core density and direct collapse into a black hole after death, without a spectacular supernova explosion. This direct collapse pathway suggests how Gaia's companion BH3 could form a black hole that's significantly more massive than those typically formed from more metal-rich progenitors. These direct observational data support broader theoretical models of astrophysics that predict that metal-poor environments favor the formation of larger black holes. These results are of great importance because they can explain the existence of supermassive black holes that appear to have formed rapidly in the early universe, refuting previous models of black hole growth that required longer timescales and multiple mergers. By studying Gaia BH3 and its stellar companion, astronomers are gaining invaluable insights into the primordial conditions of the universe, when such stars were more common. The discovery not only links past processes of star formation and death to the phenomena observed today, but also helps close gaps in our understanding of the distribution and density of black holes in the cosmos. However, science doesn't stand still. And most recently, in an amazing fusion of artificial intelligence and astrophysics, researchers led by the California Institute of Technology have pushed the boundaries of black hole observations. This team has successfully applied advanced AI technology to visualize in 3 dimensions the flares that often burst out of such objects. Using data from the Atacama Large Millimeter Array, the team focused on Sagittarius A, the supermassive black hole at the center of our galaxy. They observed flares, bright, energetic emissions that occur several times a day around black holes. These flares, although previously detected, have never been visualized in 3 dimensions until now. To achieve this goal, a team at the California Institute of Technology has developed new computational visualization tools that incorporate artificial intelligence techniques tailored to astrophysical data. These tools have been designed to solve the unique problems associated with the intense gravitational fields of black holes. A key innovation was the adaptation of a technique known as NERF, or Neural Radiance Fields, which was originally used in computer graphics enhancement. NERF helps create 3-dimensional scenes from 2-dimensional images, and the technique is ideal for astronomical data, which is usually limited to such images. By applying NERF, the researchers were able to simulate how light is bent in the black hole's immense gravity, creating a realistic model of the flare in 3 dimensions. The Dr. Katie Bauman team used a unique dataset obtained with ALMA, following an eruption near Sagittarius A observed in X-rays on April 11, 2017. ALMA collected crucial radio wavelength data for 100 minutes. This dataset was crucial in providing the fundamental observations needed for this study. The task of the AI was to reconstruct the 3-dimensional journey of gas bursting out of a black hole, despite the limitations inherent in observing such phenomena from Earth. Typically, observing celestial bodies in 3D requires the use of multiple perspectives, which is not possible when studying distant black holes. AI has bridged this gap by modeling these angles. The team used an improvised version of the NERF adapted for use in astronomy. This modified NERF was adapted to account not only for the light curvature caused by the black hole, but also for the expected behavior of the gas surrounding it. This method, similar to having a stationary camera take multiple angles of a rotating object, allowed the AI to predict the structure of the flare over time based on how the gas would move and how its light would be lensed by the black hole. The visualization showed 2 bright objects orbiting at a distance of about 75 million kilometers from the center of the black hole, half the distance between the Earth and the Sun. These objects provide tangible insight into the dynamics around black holes and confirm theoretical predictions about their behavior under extreme gravitational forces. The integration of artificial intelligence has not only involved visualization, but also physics-based machine learning. This approach uses knowledge of black hole physics to guide AI to reconstruct 3-dimensional structures from the data, taking into account the dynamic motions and transformations of the gas in the vicinity of the black hole. This technological breakthrough provides a deep understanding of the behavior and properties of matter orbiting black holes. Understanding the three-dimensional structure of these flares helps astrophysicists better understand how matter behaves under such extreme conditions, including how it moves, heats up, and eventually accretes onto the black hole. The future of black hole research is on the cusp of a new era, fueled by the latest discoveries and technological advances. Techniques developed to study black holes such as Sagittarius A and Gaia BH3 are giving astronomers powerful new tools to detect and analyze other black holes that remain hidden or dormant. Such black holes are not actively accreting material, making them incredibly difficult to detect with traditional observational methods that rely on detecting radiation from heated accreting material. Also, by mapping the environment near black holes in 3 dimensions, scientists will be able to explore fundamental questions about the nature of their gravity and dynamics. This understanding is crucial for testing the predictions of the general theory of relativity and could inform future observations and missions. In addition, each observed black hole provides valuable data about the history and structure of our galaxy. By studying the properties and behavior of black holes, especially those formed from metal-poor stars or located in unusual parts of the galaxy, such as the halo, astronomers can infer the formation and evolution of the Milky Way. This technological breakthrough sets a precedent for future astronomical observations. By merging artificial intelligence and physics, astronomers will now be able to study other celestial phenomena in unprecedented detail, paving the way for further discoveries, heralding a new era in the study and understanding of the most mysterious phenomena in the universe. The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folkloric tales, the moon holds secrets that have eluded us for centuries. Among these mysterious features is the moon's south pole, a region shrouded in perpetual shadow and intense cold, untouched and unexplored by any previous lunar mission. This is the story of Chandrayaan-3, India's daring journey into uncharted territory. Launched on a journey of more than 238,600 miles, Chandrayaan-3 embarked on a mission not just of distance, but of discovery. Its purpose? To unravel the mysteries of the moon's south pole, a place where sunlight barely reaches, an area where the terrain is so treacherous that you have to wade through an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 sought answers to questions that have puzzled scientists for decades. What lies beneath the surface of this mysterious region? Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here in the form of ice. When Chandrayaan-3 ventured beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. Its primary goal was clear, yet challenging: to achieve a soft landing near the moon's south pole, a feat that had never before been accomplished. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists and engineers piloted this ambitious mission. Their expertise helped Chandrayaan-3 traverse the space void, overcoming the challenges of lunar orbit insertion and descent. The south pole of the moon is a landscape unlike any other. Here, the terrain is a patchwork of craters and mountains, many of which are shrouded in perpetual darkness. The challenge was not just to land, but to land safely in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram landing module separated from the orbiter, it began its descent. The landing module, equipped with advanced sensors and engines, began its perilous journey to the surface of the moon. Imagine a spaceship autonomously navigating a maze of craters and boulders in search of a patch of land safe enough to land on. The landing module's onboard systems were hard at work, analyzing every inch of the terrain below. Against this treacherous landscape, The landing module also struggled with extreme temperatures. The moon's south pole is a place of stark contrasts. The sun barely rises above the horizon, while shadows hide frigid temperatures that can drop to minus 382 degrees Fahrenheit. As the landing module made its final approach, the hearts in the Flight Control Center beat harder. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a light thud, Vikram landed, marking an historic moment not only for India, but for lunar exploration in general. In the silence of the moon's south pole, Chandrayaan-3 began its mission of exploration and discovery. So, after the historic landing of Chandrayaan-3, a new chapter in lunar exploration began. The mission's goal was to maximize the study of the moon's characteristics, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just beneath its surface. The lunar exosphere, the thin layer of gases surrounding the moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, the moon's exosphere is so rarefied that it almost resembles a vacuum. The Chandrayaan-3 instruments, developed using the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delved deeper into the moon's ionosphere. This layer, formed by solar energy ionizing atoms in the exosphere, plays a crucial role concerning lunar communication and navigation. The Chandrayaan-3 measurements were designed to provide unprecedented information on the density and behavior of the ionosphere, which is important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was studying the temperature variations just beneath the lunar surface using one of 4 instruments on the landing module, CHASTE, or Chandra's Surface Thermophysical Experiment. The temperature probe, immersed in the lunar regolith, was tasked with the critical mission of mapping the thermal profile of the lunar soil. The results of Chandrayaan-3 revealed a sharp contrast in temperatures. On the surface, during a lunar day, temperatures rose dramatically to 140 degrees Fahrenheit. While just 8 centimeters deeper, they dropped significantly to 14 degrees Fahrenheit, demonstrating the lunar soil as a potential thermal insulator. This discovery provided new opportunities for future lunar habitats, suggesting that the lunar regolith could serve as a thermal insulator, protecting astronauts from the moon's harsh extreme temperatures and harmful radiation. These studies were more than just scientific endeavors. They were stepping stones toward a future in which the moon could be a gateway to future space exploration. Mission results on the lunar exosphere, ionosphere, and subsurface temperature laid the foundation for understanding the moon's environment and its potential to support human life. Standing in the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon that had not been observed for more than 50 years, a lunar earthquake. The mission succeeded in shedding light on one of the most intriguing and least understood aspects of the moon. The Instrument for Lunar Seismic Activity, or ILSA, a seismic instrument, was designed to detect the slightest tremors on the moon, and it did. Chandrayaan-3 detected what looked like a lunar earthquake, a significant discovery given that the last such observation was made during the Apollo missions in the early 1970s. Lunar quakes are fundamentally different from earthquakes. While Earth's seismic activity is largely due to the movement of tectonic plates, the Moon, which is devoid of these plates, experiences earthquakes for a variety of reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a subject of scientific interest. The Chandrayaan-3 data suggests several possible causes for these earthquakes. One theory is a collision with meteoroids, which could cause shock waves that penetrate the Moon's crust. Another is Earth's gravitational pull, causing tidal forces that load the lunar crust. And finally, extreme temperature fluctuations on the Moon's surface can cause expansion and contraction, leading to earthquakes. These earthquakes are not just surface phenomena, they're windows into the Moon's interior. By analyzing the seismic waves, scientists can infer the composition and structure of our satellite's interior, which resembles a sonogram of the lunar interior. Such information is of great importance for understanding the formation and evolution of the Moon. The detection of a lunar earthquake by the Chandrayaan-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened up new insights into the geological processes that shape the Moon. To unravel the geologic mysteries of the Moon, Chandrayaan-3 carried out another exploration. Among the most intriguing finds was the discovery of sulfur, an element whose presence on the Moon has been shrouded in mystery. The Laser-Induced Breakdown Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes tiny samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thereby revealing the presence of various elements, including sulfur. Sulfur on the Moon is a significant find. On Earth, sulfur is often associated with volcanic activity, raising questions about similar processes on the Moon in the past. Its presence could provide insight into the volcanic history of the Moon and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrayaan-3 was the search for water ice, a search that's intrigued scientists for decades. Water ice on the Moon is not just a scientific curiosity. It's a potential resource for future human missions, offering water for life support and fuel production. Despite high hopes, Chandrayaan-3, like its predecessors, found no direct evidence of water ice on the Moon's surface. However, the lack of direct evidence is not a conclusion, but a clue leading to new hypotheses. One theory is cold trapping, in which water vapor can migrate to permanently shadowed craters at the poles, freezing into ice. The detection of sulfur adds another layer to this theory, as sulfur may be trapped with the water ice and released as a result of the breakdown of water molecules by high-energy solar radiation. The lack of direct evidence for the existence of water ice raises important questions. Is the ice deeper beneath the surface, shielded from detection by the insulating properties of the lunar soil? Or is its prevalence more heterogeneous and elusive than previously thought? During its exploration of the Moon's south pole, Chandrayaan-3 found more than just sulfur. The rover's LIBS instrument made the first ever in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each element reflecting part of the complex geologic history of the lunar surface. Further measurements added new details to this discovery, further revealing the presence of manganese, silicon, and oxygen. These elements, each with its own unique spectral signature, provided clues to the formation of the Moon and its evolutionary history. Studies of the presence of hydrogen, a key component in the search for water, also continue. The mission's discovery of these elements and the ongoing search for water ice underscore the dynamic and complex nature of the Moon's geology. Each discovery, each unanswered question, moves us further in our quest to understand our nearest celestial neighbor and prepares us for the next steps in lunar exploration. As the Chandrayaan-3 mission at the Moon's south pole opened a new chapter in lunar exploration, it also paved the way for the next ambitious leap, the Lunar Polar Exploration Mission, LUPEX for short. This joint venture between the Indian Space Research Organization and Japan Aerospace Exploration Agency is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the South Pole region of the Moon. JAXA will likely provide the H-3 launch vehicle and rover under development, and ISRO will provide the lander. This mission represents a significant step in international cooperation on lunar exploration. The mission's goals are multifaceted. It will demonstrate new surface exploration technologies critical for sustained lunar exploration in the polar regions. Precise landings will be achieved by using a feature-matching algorithm and navigation equipment derived from the JAXA Smart Lander for Investigating Moon mission. The LUPEX rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples from a depth of 5 feet, 1.5 meters. Finding and analyzing water are key goals of the mission, and the potential discovery of water ice could be a game-changer for future lunar missions. In parallel with LUPEX, ISRO's Chandrayaan-4 mission, designed to return samples from the Moon, is in the planning stage. Scheduled for launch by 2028, Chandrayaan-4 will consist of 4 modules: a transition module, a descent module, an ascent module, and a re-entry module. The ambitious goal of the planned mission is to return soil samples from the Moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, including sample collection, docking in lunar orbit, and returning samples to Earth. Chandrayaan-3's innovative discoveries, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the Moon's mysterious nature. These results provide crucial insight into the Moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration is promising. Missions like LUPEX and Chandrayaan-4, building on the legacy of the previous ones, will continue to explore the mysteries of the Moon. India's role in these endeavors is not only that of a participant, but also that of a pioneer. Such events truly inspire us to look beyond the boundless mysteries of the cosmos. The solar system has served as a reliable bulwark for life. But one day, humanity will have to leave its native Earth to continue existing. In recent decades, scientists have been desperately looking into the dim depths of space in search of a haven for life. So far, none of the exoplanets we've found have refuted the hypothesis of the uniqueness of life. But what if we're simply looking in the wrong place? Perhaps it's not the planets that hold all the answers, but their moons. In the mystical deep space, exomoons are unlike any other satellite in the solar system. The size of our Earth, these hidden giants have an amazing feature. Life can be found in their interior, many times more often than on ordinary exoplanets. Today, we'll dive into the mysterious, distant universe and try to discover why exomoons may someday change humanity. Let's go back to the very beginning of the history of exoplanet science. Since astronomy received a strong impetus only in the middle of the 20th century, scientists began to study the first exoplanets not so long ago. The first confirmed exoplanets were recorded in 1992. It was a group of Earth-mass planets orbiting the pulsar PSR B1257+12. Just 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, which is dedicated to the study of planetary systems outside our solar system, and, in addition, the search for places where human-like life could originate. Other exoplanets available in our visible universe didn't have to wait long either. In the following years, astronomers found several more exoplanets, until in 2009, the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it was able to confirm about 715 exoplanets, with a size and conditions similar to Earth's. As of now, we already know about more than 5,500 planets outside the solar system, and the recently sent James Webb Telescope will likely to be able to show us even more distant planets. Further, in 2013, scientists were able to determine the planet's color for the first time, and a year later, they were able to record the magnetic field, and later, volcanic activity. Finally, in 2018, astronomers made a new, potentially breakthrough discovery. For the first time, a possible exomoon was recorded near the planet Kepler 1625b. While this may not seem like such an incredible discovery at first glance, exomoons open a new chapter in modern astronomy, not only as novel, hitherto unexplored space objects, but also as potential elements for supporting life on exoplanets and satellites themselves. Every year, knowledge about distant, dim exoplanets deepens, bringing scientists closer to a complete picture of the history of the entire universe. But how did the scientists manage to confirm so many planets in such a short time when it's impossible to take a photo of each one? Only 69 planets were found with images. The most popular method is the transit method, which you may already know. When an exoplanet passes by its central star, the same star becomes slightly dimmer, which reveals the presence of an object orbiting it. Although this method doesn't allow us to directly observe the planet, and may turn out to be just a glitch, it is currently the most effective of all. Exoplanet exploration plays a crucial role in all of astronomy and the future of all of humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exosatellites are of not much interest to current research. The main problem associated with the search for these exoplanets is their elusiveness to telescope radar. Although no scientists deny that some exoplanets may have satellites, it's an extremely difficult and, to some extent, even impossible task for our current technologies to investigate them. The transit method, or more precisely, the method of studying the shift in the spectrum of stars, can confirm an exoplanet. But a satellite orbiting it? Almost under no circumstances, unless, for example, the spacecraft is in the closest possible proximity to the object of observation due to a completely insignificant change in the brightness of the star. Thus, even the very first exomoon found by Kepler and the ones discovered later near the planets Kepler 1708b and Kepler 1513b are still not perceived as full-fledged proof of their existence, and therefore there is a possibility that it could be just some kind of technical error during the observation, which is not so far from the truth, since further observations did not yield any encouraging results. However, as in the case of the giant planet satellite Kepler 1625b, an exomoon can be seen if it is large enough. So far, the first hypothetical exomoon could be the size of the Earth and have a strange tilted orbit like Neptune's moon Triton. Such a huge size of a possible moon may become one of the most important elements in the further search for other moons. Thus, more than 20 exomoon candidates are currently known. All of them are gigantic. Probably at least for Kepler 1625b, it's the star around which it orbits. It is a red giant. This dying star can heat the moon's atmosphere, increasing its effective diameter and allowing scientists to detect satellites more often. However, perhaps right now, exomoons are not of too much scientific importance for scientists to invest a lot of resources in developing technologies to find them. At this stage of our science, exomoons don't seem to be a higher priority than other space objects, such as exoplanets. The satellites of distant planets are too complex to study and have a very high chance of a false positive result. Therefore, it may take months or even years of observation and analysis to confirm one satellite, when it seems more rational to spend this resource on exploring a planet with potential support for life, including human life. Of course, it is possible that exomoons may hide life in their interior, but alternatives in the form of rocky exoplanets like Earth are still of much higher importance in scientific circles. But we're going to focus on the exomoons themselves and try to investigate them. Is there any need to study these mysterious and hidden moons at all? In fact, these moons contain a lot of information for our complete understanding of the structure of the universe. But this will only be possible in the future, albeit not in the near future. The first thing that draws scientists' attention to even just candidates for exomoons is their size. The largest moon in the solar system, Ganymede, orbiting Jupiter, has a diameter of 3,273 miles, or 5,268 kilometers. But recorded exomoons can reach the size of the Earth, or even Neptune. Therefore, since such moons are even difficult to distinguish among exoplanets, it's incredibly exciting to imagine what moons might look like and what activity they exhibit. It's possible that some large exomoons have many of the features of planets, and that their study could overturn everything we know about satellites. Their similarities to other exoplanets, such as their likely geologic activity, bring us to the next important point for careful study in the future. and that is the support of life. We know that several moons of the solar system, such as Enceladus or Europa, despite their low surface temperatures and small size, could, hypothetically, be a haven for living organisms due to the presence of global oceans. However, what about the much more massive moons, which not only can support a dense atmosphere, but also have more access to building chemicals, both from the inside and outside? According to a study by the University of Washington, exomoons have more potential to support life than even exoplanets. They also have a habitable zone, although it's slightly different. But the main argument for exomoons as one of the most intriguing places for life to exist is the availability of several heat sources for them. The first source is the star itself, and the second is their planet. The moons are heated by the gravitational pull of the planet, which keeps the probable water in the interior of the moon in a liquid state. Moreover, heating from an exoplanet can stimulate geological activity, such as volcanic eruptions, creating enough gas inside the moon to maintain an atmosphere for a long time, and also bringing various crucial chemical elements to the surface. So exomoons are not as simple as they may seem. Perhaps the difficulty of finding them will be rewarded with a potential breakthrough in science. Finally, exomoons may become the necessary tool to study the formation of our universe. Thus, the analysis of exomoons near different stars and planets can reveal to scientists how space objects are formed, what factors are responsible for supporting life, and what the history of other planetary systems is in general. In particular, comparing the moons of the solar system with those of distant systems can give scientists an understanding of the specifics and conditions of their development, as well as an approximate value of the abundance of systems where complex intelligent life has developed. The Earth, hypothetically, may be almost the only planet on which life could have formed, at least in the visible universe. And any clues on exomoons with potentially higher chances of supporting living organisms can confirm or deny this. However, for now, deep exploration of exomoons is only a matter of the future. On the other hand, the James Webb Space Telescope mission will continue for several more years, so perhaps the hope of finding an exomoon for the first time in this decade is not going away. Nevertheless, since the search for exomoons is an extremely difficult and almost impossible task for our current technologies, exomoons are likely to become one of the drivers of technological progress. As we know, the transit method or gravitational lensing will not help to look for microsigns of the presence of exomoons, so this factor is already challenging scientists to modify or even create new technologies to capture such subtle objects. But this is a task for the near future. In the long term, both intriguing moons and exoplanets will require much more thorough analysis, including using images and samples of the atmosphere or even soils. So, if interesting candidates where extraterrestrial life exists are ever found, then comprehensive space missions are likely to follow, advancing human knowledge of the research focus. The only step we have left to take is to find such an exoplanet or exomoon. In 2026, the European Space Agency plans to send the Plato mission, which will continuously look at several areas in outer space to capture transiting objects. The mission will last for 6 years and may be the one to make this expected discovery. However, the benefits of exomoon search and exploration do not end with a technological breakthrough. Exomoons are very valuable natural laboratories located near various planets and stars. Analyzing the impact of these bodies on the moons will not only deepen what's known about the formation of planets, but also demonstrate to scientists the variety of conditions under which life can develop. For example, traces of bio or even techno-signatures created by civilizations on various moons can provide a clearer picture of the signs for the development of intelligent life, thus building more prioritized paths for future missions to the most likely planets or moons for aliens to live on. But for now, we can only wait for the moment when we find the first exomoon and begin a long but life-changing scientific and technological ascent. Exomoons, despite their invisibility and skeptical insignificance, may one day critically change everything known to the entire human race about our vast universe. Even a small observation can eventually become the main driver for revolutionary discoveries. Continued research will reveal more and more answers, and only by pursuing this knowledge will the cumbersome, mysterious cosmos one day become less confusing to us. But in the face of the vast universe, we must never lose our enthusiasm for learning, no matter how difficult and distant our desired outcome. Mercury is an enigmatic planet. Despite being closest to the Sun, it's still the least known to us. Often overshadowed by its neighbors, it's a world of mystery waiting to be revealed. What if Mercury isn't what we thought it was? Recent discoveries indicate that this planet is more dynamic and complex than anyone imagined. From shrinking landscapes to mysterious blue troughs, Mercury is challenging everything we know about it. Imagine a planet rushing around the Sun at breakneck speed, a world so close to the solar furnace that it's hard to even get close to it. Few missions have dared to visit this elusive world, and those that have discovered only glimpses of its secrets. However, a new mission, Bepi Colombo, promises to unlock mysteries that have puzzled scientists for decades. Already we're seeing things that defy explanation, strange features, unexpected phenomena, and hints of a story yet to be told. Mercury's X-ray auroras, its changing topography, and its hidden interior all suggest that the planet is far more intriguing than we ever thought. Prepare to see Mercury in a whole new light. It's not just a planet, it's a mystery at the edge of the Sun. Mercury, the innermost planet, orbits closest to the Sun. It's the smallest planet, slightly larger than our Moon, and takes only 88 Earth days to complete one orbit. Because of its proximity to the Sun, Mercury experiences temperature extremes ranging from scorching highs of 800 degrees Fahrenheit to icy lows of minus 290 degrees Fahrenheit overnight. Its surface is a mosaic of craters, ridges, and plains. Unlike other planets, it has no significant atmosphere to protect it from meteoroids, resulting in a landscape heavily riddled with craters and reminiscent of our Moon. One of the most striking features is the Callisto Basin, one of the largest impact craters in the solar system. This massive basin, about 960 miles in diameter, was formed by a colossal impact early in Mercury's history. Another unique aspect of Mercury is its unusually large core, which makes up about 85% of the planet's radius. This iron-rich core generates a magnetic field, but it is only 1% as strong as Earth's. Despite its weak magnetic field, Mercury has magnetic poles and a magnetosphere that interacts with the solar wind, creating phenomena such as the recently discovered X-ray auroras. Exploring Mercury presents significant challenges. Mercury's proximity to the Sun means that spacecraft must withstand intense solar radiation and heating. In addition, Mercury's fast orbit requires precise and energy-intensive maneuvers to enter its orbit. In 1973, NASA launched Mariner 10, the first spacecraft to visit Mercury. Mariner 10 utilized the gravitational assistance of Venus, allowing it to make 3 flybys of Mercury between 1974 and 1975. These flybys produced the first close-up images of the planet's surface, showing the planet's heavily cratered terrain and complex geologic features. The spacecraft's images showed a world similar to our Moon, with vast plains and numerous impact craters. However, the mission captured only 45% of the planet's surface, leaving much unexplored. Despite the limited coverage, the mission data laid the groundwork for future research. Decades later, the Messenger spacecraft, launched by NASA in 2004, became the first spacecraft to orbit Mercury. After a challenging journey that included flybys of Earth, Venus, and Mercury itself, the spacecraft entered its target orbit in 2011. During its 4-year mission, Messenger made more than 4,000 revolutions around the planet, collecting a wealth of data on the planet's surface, composition, and magnetic field. Messenger showed Mercury's surface in unprecedented detail, mapping almost the entire planet. It revealed volcanic plains, evidence of past tectonic activity, and gave a glimpse of the planet's thin exosphere. One of the most surprising discoveries was the presence of water ice in permanently shadowed craters at Mercury's poles, even though the planet is close to the Sun. Building on the successes of Mariner 10 and Messenger, the Bepi-Colombo mission represents a significant step forward in Mercury exploration. The mission is a joint effort between the European Space Agency and the Japan Aerospace Exploration Agency. Launched in 2018, Bepi-Colombo should provide comprehensive data on the geology, atmosphere, magnetosphere, and history of Mercury. Bepi-Colombo consists of 2 main spacecraft, ESA's Mercury Planetary Orbiter and JAXA's Mercury Magnetospheric Orbiter, also known as MAIO. Together, these spacecraft will study the planet from different perspectives, offering a holistic view of its evolution and environment. The mission's journey to Mercury will be long and complex, involving many gravity assist systems. Bepi-Colombo has already made flybys of Earth in 2020 and Venus in 2020 and 2021. It will make 6 flybys to Mercury before entering orbit in December 2025. These flybys are critical to adjust the spacecraft's trajectory and slow it down enough to be captured by Mercury's gravity. The goals of Bepi-Colombo are ambitious. The mission should map the planet's surface in high resolution, analyze its composition, and study the magnetic field and magnetosphere. It will also study the planet's exosphere and search for evidence of past volcanic and tectonic activity. By comparing data from both orbiters, scientists hope to gain new insights into the formation and evolution of Mercury, as well as its mysterious magnetic field. So since its launch in 2018, Bepi-Colombo has been steadily approaching Mercury, making a series of flybys that have already yielded significant results. These preliminary observations provide new insights into Mercury's complex geology and dynamic environment. One of the key contributions of the mission was the detailed mapping of Mercury's surface. The spacecraft discovered many previously unknown craters, each telling a different story of the planet's turbulent past. Among them are impact basins that show the scars of ancient collisions, shedding light on the early chaotic period of the solar system. One of the mission's most intriguing discoveries is the detection of X-ray auroras around the planet. Unlike visible terrestrial auroras, Mercury's auroras are detected in the X-ray spectrum. This phenomenon was first hinted at by the Messenger mission, and now it's been confirmed by Bepi-Colombo. These X-ray auroras are caused by the interaction between Mercury's magnetic field and the solar wind, a stream of charged particles emitted by the Sun. When these particles collide with the planet's surface, they generate X-rays, causing a faint but scientifically valuable glow. This discovery not only confirms the presence of a magnetosphere, but also provides insight into the nature of Mercury's magnetic field and its interaction with the solar wind. Another important recent discovery was confirmation that Mercury continues to shrink. High-resolution images have revealed features such as lobate scarps and wrinkle ridges, which are formed by the compression of the planet's crust as its core cools and hardens. These results build on observations made by the Messenger mission and provide clear evidence of Mercury's ongoing geologic activity. The planet's compression has caused its radius to shrink by several kilometers since its formation, creating stress cracks on the surface that manifest themselves as ridges and cliffs. Bepi Colombo, in turn, has identified several regions where this contraction is most obvious, providing a unique opportunity to study planetary geology in real time. These regions reveal not only Mercury's cooling history, but also its current state, giving scientists clues about the planet's internal structure and thermal evolution. At first glance, Mercury's heavily cratered surface resembles that of our Moon. Both bodies are riddled with impact craters, indicating a long history of collisions with asteroids and comets. However, a closer look reveals significant differences. Mercury's craters are often interspersed with ridges and fault scars, which are less common on the Moon. These scars are indicative of Mercury's compression, a process not observed on the Moon. In addition, there are areas on Mercury's surface with fewer boulders than on the Moon, suggesting different geologic processes. One of Mercury's most enigmatic features is its depressions. First discovered by the Messenger mission, they're irregular, shallow depressions, often surrounded by bright halos. Their formation has puzzled scientists since their discovery. Initially, the researchers hypothesized that these depressions might be of volcanic origin. They considered the possibility that volcanic processes had left behind these unusual formations. However, the distinct appearance of the depressions and the lack of associated volcanic features prompted further investigation. According to current thinking, Mercury's troughs were formed by sublimation, a process by which solid materials are converted directly into gas. This process probably involves volatiles beneath Mercury's surface. When these volatiles sublimate, the surface erodes, forming the sinkholes and bright halos seen around the depressions. These data suggest that despite its proximity to the Sun, Mercury stores volatile compounds just beneath its surface. Continued sublimation and the formation of depressions indicate that the planet is still a geologically active world, contrary to previous beliefs. Mercury's proximity to the Sun and the extreme temperatures of its surface led scientists to believe that it was devoid of volatile compounds. However, recent discoveries have dramatically changed this view. High concentrations of sulfur, chlorine, sodium, and potassium have been found on Mercury's surface that indicate the presence of volatile-rich layers extending several kilometers deep. The discovery of sublimation depressions with a flat bottom and bright interior and halo indicates the existence of volatiles beneath Mercury's surface. These depressions form when volatile materials sublimate, causing the surface to erode into sinkholes. This ongoing geologic process suggests that Mercury is still losing volatiles, which changes our understanding of its geologic history and activity. Sublimation leads to another very fascinating event occurring on the planet: its sodium tail. Observations have shown that Mercury emits a tail of sodium atoms, making it, in a sense, similar to a comet. This phenomena is caused by solar radiation and solar wind, throwing sodium atoms from Mercury's surface into space. The sodium tail extends millions of miles into space, and it's a clear indicator of the ongoing release of volatiles from the planet's surface. This tail is not visible to the naked eye, but can be detected with specialized instruments, allowing us to learn much about Mercury's exosphere and the processes that contribute to its formation. Interestingly, the volatile content of Mercury has been compared to some of the most extreme environments on Earth, such as the Atacama Desert in Chile. Both regions have high concentrations of salts and other volatiles, despite very different environmental conditions. The Atacama Desert is known for its extremely dry conditions and high salt content, which support unique extremophiles, organisms that thrive in extreme conditions. Research indicates that similar conditions may exist beneath the surface of Mercury. where salts and other volatiles can create niches for potential microbial life, albeit under much more extreme conditions. Extremophiles in the Atacama Desert survive in highly saline and dry conditions, suggesting parallels with potential habitats on Mercury. These microorganisms have adapted to live in niches with minimal water and high salt concentrations, suggesting that life could potentially exist in similar conditions on Mercury. If Mercury has a volatile-rich subsurface, it's also possible that this environment could provide the necessary conditions for life, at least in microbial form. The presence of halides and other salts could lead to the formation of liquid water through a process of deliquescence, where salts absorb moisture from the atmosphere, even in small amounts, potentially supporting microbial communities. The origin of Mercury has long puzzled scientists. According to traditional theories, it formed not far from its current position. However, a considerable amount of recent research agrees that Mercury could have started its journey much farther from the Sun. One of the leading theories is planetary migration, where, early in the history of the solar system, gravitational interactions caused significant shifts in planetary orbits. Mercury could have formed in the outer regions of the solar system, rich in volatile matter, and migrated inward over time. Evidence in favor of this theory comes from Mercury's unusual density and its large iron-rich core. According to recent studies, Mercury's core is about 85% of its radius, which is much larger than any other terrestrial planet. Some scientists speculate that Mercury was once a much larger planet, similar in size to Mars, with a thick mantle and crust. A catastrophic collision with another large body could have stripped Mercury of most of its outer layers, leaving behind a dense core and thin mantle. This hypothesis would explain Mercury's high density and the presence of high levels of some elements, such as thorium and potassium, that are commonly found deep in planetary interiors. The giant impact theory is supported by Mercury's geologic features. The planet's surface is marked by impact craters and basins, such as the Callisto Basin, one of the largest impact structures in the solar system. This collision theory is consistent with observations of other celestial bodies and their histories. Similar collisions are thought to have led to the formation of the Moon and caused significant changes in other planets, suggesting that Mercury's history may be part of a larger pattern of planetary evolution in the solar system. The discovery of bainite, a rare type of volcanic rock on Mercury, is also intriguing evidence. Bonanite is typically rich in magnesium and low in other elements, indicating that it formed under special conditions associated with high temperatures and pressures. Geologists have found similar rocks in Cyprus, suggesting a common formation process. They appear white in the images because bonanite oxidizes in Earth's oxygen-rich environment. These terrestrial analogs provide insight into Mercury's volcanic history and support the idea that its mantle has undergone significant melting and differentiation. On Cyprus, bonanite is associated with ancient tectonic processes when the oceanic crust was pushed deep into the mantle and partially melted. The presence of similar rocks on Mercury suggests that it too has undergone intense geologic processes, possibly related to a hypothetical major collision and subsequent migration. By comparing geologic formations on Mercury with those on Earth, scientists can piece together the story of Mercury's formation and evolution. Features such as fault lines, ridges, and volcanic plains on Mercury resemble those in tectonically active regions on Earth. These comparisons show that despite its small size and proximity to the Sun, Mercury has a dynamic and complex geologic history. Studying Mercury's geology not only helps us understand its past, but also provides insight into the processes that have shaped other rocky planets in our solar system. As Bepi Colombo approaches its destination, scientists are looking forward to the vast amount of data it will provide. The mission's expected to provide detailed maps of Mercury's surface, study its magnetic field, and provide new information about its geologic history. Although the search for life on Mercury is unlikely, the discovery of volatiles and potentially subsurface environments offer intriguing possibilities. Extremophiles on Earth thrive in harsh environments, hinting that similar life forms could exist on Mercury, given the right conditions. Mercury occupies a unique place in planetary science. In the broader context of solar system studies, this planet serves as a key to unraveling the history and evolution of the terrestrial planets. Its study helps us understand the processes that have shaped not only our solar system, but perhaps the rest of the solar system as well. As we look forward to the next wave of discoveries, Mercury promises to remain the center of scientific inquiry, offering endless opportunities to learn more about the universe and our place in it. Have you ever heard of a galaxy that defies categorization? Imagine a cosmic structure that combines an ancient dormant core surrounded by a bright halo of young stars. This is not your typical spiral or elliptical galaxy, but something much more mysterious. A Hogue object. Initially mistaken for a planetary nebula or gravitational lens, the true nature of Hogue's object remained hidden until more advanced observations revealed its unique structure. The central elliptical core appears red and inactive, while the outer ring is bright blue, teeming with new star formation. A clear gap separates the two components as if they belong to different galaxies. The object spans an impressive 121,000 light-years wide, with a central core about 17,000 light-years across and an outer ring stretching out 75,000 light-years. This apparent gap between the core and the ring is wider than the ring itself, which is a surprising feature for such a colossal galaxy. Ring galaxies, like Hogue's object, are extremely rare, making up less than 0.1% of all known galaxies. They often arise from complex cosmic events, but Hogue's object seems to maintain a calm and orderly appearance, which further deepens the mystery. Despite decades of research, astronomers are still grappling with the question of the origin of this galaxy. Was it the result of a quiet accretion process, or did a cosmic collision play a role? Arthur Hogue, a prominent astronomer of the mid-20th century, made a discovery that would intrigue and puzzle scientists for decades to come. In 1950, while conducting a study of the night sky, the astronomer came across a celestial object that defied conventional classification. This object, later named after him, had characteristics unlike any previously observed galaxy. At first glance, Hogue's object appeared to be a planetary nebula, a cloud of gas and dust surrounding a dying star. However, its unusual structure, consisting of a central core surrounded by a luminous ring, suggested otherwise. Early images taken by the astronomer's telescope showed a clear separation between the inner and outer components, prompting curiosity and speculation. Initial hypotheses varied widely. Hogue himself hypothesized that it could be a planetary nebula, or even a gravitational lens. The gravitational lens hypothesis suggested that the object was not a galaxy at all, but rather a massive elliptical galaxy magnifying a background galaxy in a ring-like shape. Gravitational lenses occur when a massive object, such as an elliptical galaxy, bends the light of a more distant object behind it. This bending creates a ring of light around the foreground object, known as the Einstein ring. In early observations, the outer ring of Hogue's object resembled such a lens, suggesting that it may be a foreground galaxy amplifying the light of a more distant object. For nearly 4 decades, the true nature of the Hogue object remained uncertain. It was not until 1987 that astronomers equipped with better technology were able to confirm the connection between the ring and the nucleus through spectroscopic analysis of the red shift. This shift is due to the expansion of the universe, with more distant objects exhibiting a greater redshift. By analyzing the redshift of the core and ring of Hoag's object, astronomers confirmed that they're not separate entities, but components of the same galaxy. This discovery debunked the gravitational lens hypothesis and cemented the status of the Hoag object as a unique type of galaxy. The central core, consisting of old red stars, contrasts sharply with the outer ring, which is bright blue and actively forming new stars. It is this special composition and structure that distinguishes Hoag's object from typical spiral and elliptical galaxies. Ring galaxies are rare, making up less than 0.1% of all known galaxies. Typical spiral galaxies have sprawling arms of stars, while elliptical galaxies have a more uniform, rounded shape. The Hoag object, with its perfectly separated nucleus and ring, remains one of the most well-defined examples of this rare class of galaxies. The discovery began the scientific journey to understand one of the most mysterious structures in the universe. Today, with the help of modern telescopes and ongoing research, astronomers are trying to unravel the mysteries surrounding this fascinating cosmic anomaly. Its quiet appearance, distinct breakup, and combination of an ancient core with a young, star-forming ring make Object Hoag a unique and enigmatic galaxy, prompting astronomers to investigate various theories of its origin and evolution. Thus, one of the main theories proposed to explain the formation of the Hoag object is the collision hypothesis. According to this theory, the characteristic ring structure of the galaxy arose as a result of a high-speed collision of a smaller galaxy with a larger one. When a smaller galaxy collides with a larger galaxy, the impact generates a density wave that rushes outward from the center of the larger galaxy. This wave compresses the interstellar gas, causing star formation in the ring around the galaxy's nucleus. The Cartwheel galaxy, with its strikingly similar ring structure, is a classic example of this process. In the case of a Hoag object, if a smaller galaxy collided with it, we would expect to detect several key features. First, the collision would create density waves that push the gas and stars outward, forming a ring. Moreover, the stars in the ring should have exhibited high relative velocities, indicating the kinetic energy from the collision. And third, in or near the ring, there would be residual fragments or remnants of colliding galaxies. However, detailed observations of Hoag's object have revealed some inconsistencies with the collision hypothesis. The ring stars do not exhibit the high relative velocities that are usually associated with such events. In addition, there's a notable absence of residual fragments or evidence of a second galaxy. To test this hypothesis, models of galaxy collisions have been used. These models show that although a collision may produce a ring structure, the resulting galaxy often retains traces of violent interaction. The Hoag object, which has a calm and symmetrical appearance, lacks these chaotic features, suggesting a more complex formation history. However, another intriguing possibility looms on the horizon: resonance theory. Could a galaxy's ring structure be the result of gravitational interactions within a spiral galaxy? Let's explore this question. Another fascinating theory explaining the formation of the Hoag object is the resonance theory. According to this theory, the ring structure of a galaxy can arise as a result of the internal dynamics of barred spiral galaxies, in particular due to resonance in the gravitational field. Spiral galaxies are characterized by the structure of a central bar, from the ends of which spiral arms branch off. These bars play a crucial role in the dynamics and evolution of the galaxy. According to theory, as the bar rotates, it can create a resonance that affects the distribution of gas and stars within the galaxy. Resonance occurs when gravitational forces within a galaxy create regions in which the rotational velocities of stars and gas clouds synchronize. These regions can trap gas and stars, resulting in the formation of rings. There are several basic types of resonances. Inner Lindblad resonance occurs near a galaxy center, often forming an inner ring. Outer Lindblad resonance arising further, potentially forming an outer ring. The third type is co-rotation resonance, a region where the rotational velocity of the bar coincides with the orbital velocity of the stars and gas, which can also lead to ring formation. In the case of the Hogue object, the presence of a ring around the elliptical core suggests that such resonances may have played a role in its formation. The bar structure could have caused a resonance that trapped gas and stars at certain radii, creating the distinct ring we see today. When the bar rotates, it exerts a gravitational influence that can reorganize the gas and stars of the galaxy. Over time, this process can lead to the formation of a well-defined ring structure. Resonance theory provides a mechanism for how a spiral galaxy can evolve into a ring galaxy without a collision. NGC 1291 is a classic example of a galaxy in which resonance effects likely played a role in ring formation. The central band and outer ring provide a visual analogy of what may have happened in Hogue's object. However, the resonance theory faces difficulties when applied to the Hogue object. In particular, the Hogue object currently has no central bar. This absence raises the question of whether the bar may have existed in the past and subsequently dissipated, or whether other processes may have contributed to the formation of the ring. However, there is another interesting and equally plausible theory, the accretion theory. Can the gradual accumulation of intergalactic gas explain the unique structure of the galaxy? Let's explore this in more detail. The third major theory proposed to explain the formation of the Hogue object is the accretion theory. According to this theory, the unique structure of the galaxy resulted from the gradual accumulation of intergalactic gas, rather than from a dramatic collision or internal resonance. Accretion is the process by which a galaxy collects gas from the surrounding intergalactic medium over a long period of time. This gas is entrained by gravitational attraction, gradually accumulating and forming new structures. In the case of the Hogue object, it's likely that a central elliptical core formed first. Over time, the gravity of this core attracted gas from the intergalactic medium. As the gas approached the nucleus, it began to rotate around it, forming a ring structure due to angular momentum conservation. As gas accumulated in the ring, its density reached a high enough density to trigger star formation. This process explains the bright blue color of the ring, indicating active, ongoing star formation. And the gap between the core and the ring is explained by the balance of gravitational forces and the dynamics of the infalling gas. Galaxies such as NGC 6028 provide an example of how accretion can lead to the formation of ring structures. These galaxies show similar features: older central nuclei and younger rings of star-forming regions, which supports accretion theory as a plausible explanation. While the accretion theory provides a plausible explanation, it also raises questions. Why does the ring form at a particular radius? How did the dynamics of gas influx and star formation balance create such a clear separation between the core and the ring? These questions continue to drive research and exploration. Continued observations have provided evidence to support this theory. The ring of Hogue's object contains more gas mass than the entire Milky Way, suggesting significant accretion of intergalactic material. In addition, the well-defined structure of the ring and the absence of chaotic remnants are consistent with a gradual and orderly accretion process. Recent research has also significantly deepened this theory. By modeling the gravitational interaction in such ring systems, scientists have shown how the balance of forces can create stable and unstable orbits, leading to discontinuities in the distribution of matter. These results are consistent with the observed structure of the Hogue object, where the gap between the core and the ring is a region of unstable circular orbits, further supporting the theory. Also, the accretion theory offers a quite convincing explanation for the formation, suggesting that the galaxy grew and evolved through the slow accumulation of surrounding gas. This process contrasts with the more violent and destructive events described in the collision and resonance theories. However, each of these proposed theories, collision, resonance, and accretion, has their own flaws, leaving several unanswered questions. Although the collision hypothesis explains the formation of the ring by density waves created by galaxy collisions, it does not explain the ordered structure of the object and the absence of residual fragments and high relative velocities commonly observed in such events. Resonance theory, on the other hand, suggests that internal gravitational resonances within a twisted spiral galaxy can create ring structures. However, it's clear that Hogue's object lacks the central bar necessary for this process, and the theory does not fully explain the apparent gap between the nucleus and the ring. Accretion theory, in turn, argues that the gradual accumulation of intergalactic gas forms a ring. While this explains the ordered structure and ongoing star formation, questions arise as to why the ring forms at a particular radius, and how the dynamics between the core and the ring create such a distinct gap. Despite these theories, several mysteries remain. Why is there a significant gap between the nucleus and the ring? What specific conditions led to the formation of such a well-defined structure? And how do gravitational forces and dynamics within the galaxy interact to maintain this balance? Future telescope missions, such as the Nancy Grace Roman Space Telescope and the soon-to-be-launched Extremely Large Telescope, are designed to provide a deeper understanding of such questions. These advanced observatories will provide higher resolution images and more detailed spectroscopic data, potentially revealing the processes underlying the formation of such ring galaxies. As we explore the cosmos, Hogue's object remains a testament to the diverse and complex processes that form galaxies, and remind us once again that there are still mysteries in the cosmos waiting to be discovered. There are few places in our solar system as mysterious as Jupiter, but recent advances in space observations have unlocked some amazing secrets of this colossal gas giant, buffeted by endless storms and cyclones. Today we're going to talk about some of the recent discoveries made by the James Webb Space Telescope and NASA's Juno mission. In this world where storms have raged for more than 3 centuries, where winds penetrate in the most intricate and unexpected ways, and where the largest vortex in our solar system may not be as old as we thought. These discoveries offer a glimpse into Jupiter's complex and dynamic atmosphere. Join us to learn about discoveries that are rewriting the history and understanding of this majestic planet. Let's start with the fact that the James Webb Space Telescope recently discovered unexpected and intriguing shapes above Jupiter's Great Red Spot, a storm that's been raging for more than 3 centuries. These previously unseen structures, observed with a near-infrared spectrograph instrument, have captured the scientific community's attention by revealing the complexity and dynamism of Jupiter's upper atmosphere. At first glance, the atmosphere above the Great Red Spot may seem unremarkable, but the sensitive infrared capabilities of JWST have shown otherwise. Scientists have detected complex patterns including dark arcs and bright spots that challenge our previous assumptions. These features are likely caused by powerful atmospheric gravity waves, a phenomenon in which waves generated in Jupiter's turbulent lower atmosphere propagate upward, altering the structure and radiation of the upper layers. Atmospheric gravity waves are something akin to waves on a beach on Earth that create ripples in the sand, but are much more intense on Jupiter, where they shape the gas giant's upper atmosphere in ways we're only beginning to understand. The tremendous energy and turbulence of the Great Red Spot generate these waves, which then travel upward, affecting the dynamics of the atmosphere. JWST observations have shown that the atmospheric structure over the Great Red Spot consists of different heights, with some regions emitting more infrared light due to the presence of hydrogen in Jupiter's ionosphere. This differentiation in heights and emission is a direct result of the influence of gravitational waves. The region above the Great Red Spot is where Jupiter's lower atmosphere meets its magnetic field. Much like Earth's atmosphere meets the solar wind, resulting in spectacular auroras. On Jupiter, this interaction is further complicated or enhanced, you might say, by volcanic material from Io, the most volcanically active body in our solar system. These materials, combined with charged particles from the Sun, fuel the Jupiterian auroras and contribute to the complex atmospheric dynamics we observe. Further study of these gravitational waves is expected to provide a deeper understanding of the energy distribution across Jupiter and enhance our understanding of its atmospheric processes. Future missions, such as the European Space Agency's Jupiter Icy Moons Explorer, or JUICE as it's known, will build on these findings. Launched in 2023, JUICE should reach Jupiter by 2031, where it will make detailed observations of the planet and its ocean-bearing moons. Another ongoing mission, NASA's Juno mission, has made another groundbreaking discovery. Jupiter's atmospheric winds permeate the planet in cylindrical layers aligned with the axis of rotation. This discovery changes our understanding of the atmosphere and internal structure of the gas giant, disproving long-held assumptions and providing new insights into the dynamics of planetary atmospheres. By analyzing data from the spacecraft's radio signals, scientists measure minute changes in Juno's speed as it orbits Jupiter. These changes, influenced by fluctuations in Jupiter's gravitational field, allow researchers to peer beneath the planet's turbulent cloud cover. Using high-precision measurements, scientists applied a mathematical method commonly used for rocky planets to model Jupiter's gravitational fluctuations. This innovative approach increased the resolution by a factor of 4 over previous models, and provided a detailed view of Jupiter's atmospheric winds. This study shows that Jupiter's powerful east-west zonal winds, observed in the planet's colorful belts and zones, do not propagate radially in all directions. Instead, they penetrate in cylindrical layers, oriented parallel to Jupiter's axis of rotation. The cylindrical nature of the winds was confirmed by comparing 40 gravity coefficients measured by Juno with theoretical models. This discovery marks a significant advance in our understanding of the atmospheric dynamics of Jupiter and similar planets. The cylindrical structure of the winds suggests a more complex interaction between the deep atmosphere and internal planetary processes. Unlike Earth's zonal flows, which are influenced by surface and topography, Jupiter's winds extend deep into its interior, unaffected by solid boundaries. These winds reach a depth of about 1,860 miles, or 3,000 kilometers, beneath the cloud tops, much deeper than previously thought. And this has profound implications for our understanding of the gas giant's internal structure and the distribution of energy within the planet. But let's get back to JWST, whose news flow never ceases. the telescope has once again revealed unprecedented details about Jupiter's atmosphere. This time, researchers have detected a high-speed jet stream passing over Jupiter's equator above the main cloud decks. This jet stream, more than 3,000 miles wide, further updates our understanding of the complex dynamics of the planet's atmospheric layers. Using NIRCam, scientists have detected this jet 12 to 21 miles above Jupiter's cloud tops. The jet has a speed of 320 miles per hour, which is twice the speed of a Category 5 hurricane here on Earth. The discovery casts new light on how Jupiter's atmospheric layers interact, revealing the complexity of the gas giant's weather systems. Jupiter, like Earth, has a multi-layered atmosphere. However, the dynamics of the gas giant's atmosphere are much more intense. The newly discovered jet stream is located in Jupiter's lower stratosphere, just above the tropospheric haze. This position allows it to influence the weather patterns and cloud formations we observe in the equatorial region of the planet. By capturing images in the near-infrared wavelength range, JWST can observe altitudinal layers with surprising clarity. These observations revealed several wind shears, areas where wind speed changes with altitude or distance that allowed researchers to trace the motion of the jet stream. The JWST data, taken at 10-hour intervals, equal to 1 day on Jupiter, provided a detailed snapshot of atmospheric changes. Additional Hubble Space Telescope observations taken 1 day after the data from JWST played a crucial role in determining the baseline of Jupiter's equatorial atmosphere. While Hubble's observations focused on the lower layers, JWST's near-infrared capabilities provided a detailed look at the high-altitude features. This dual perspective allowed scientists to measure how wind speeds change with altitude and reveal the presence of significant shifts. The detection of the jet stream was unexpected, as previous observations by ground-based telescopes and missions such as Juno and Cassini had not revealed such detailed features. The researchers intend to continue observing Jupiter with JWST to determine if the speed and height of the jet stream change over time. Lee Fletcher of the University of Leicester suggests that the strength of the new jet may be related to variations in the planet's stratosphere and could change significantly over the next few years. This ongoing study may reveal more information about the cyclical dynamics of the gas giant's atmosphere. Jupiter's Great Red Spot, the largest and oldest known storm in the solar system, has long been a subject of fascination and mystery. Recently, new theories have emerged that challenge our understanding of this iconic atmospheric formation, suggesting that the Great Red Spot we see today may not be the same storm observed centuries ago. In 1665, Italian astronomer Giovanni Cassini recorded a giant dark spot on Jupiter, which he called the permanent spot. This feature, perhaps first noted by English scientist Robert Hooke a year earlier in 1664, disappeared from observations by 1713. For many years, astronomers believed that the permanent spot was the same as the modern Great Red Spot, first observed in 1831 at the same latitude. However, a recent study led by Agustin Sanchez La Vega of the University of Basque Country suggests otherwise. After analyzing the size and movement of these vortices over time, the researchers concluded that it's highly unlikely that the current Great Red Spot is the same as Cassini's so-called permanent spot. Most likely, the original storm disappeared between the mid-18th and 19th centuries, making the current Great Red Spot a younger formation, with a lifespan of more than 190 years. Using historical data, Sanchez La Vega and his team performed a computer modeling to figure out how the Great Red Spot might have formed. The leading theory is that wind instability in Jupiter's atmosphere created the elongated atmospheric cell we see today. This process involves a complex interaction between the planet's high-speed winds and the dynamics of the atmosphere. One of the most significant observations of the Great Red Spot is its constant shrinking. In 1879, the size of the spot was about 24,200 miles along its longest axis. Today, it's only 8,700 miles long. This dramatic decrease in size raises questions about the storm's future. Will the Great Red Spot eventually disappear, as Cassini's so-called permanent spot did? The research team plans to conduct further modeling to predict the fate of the Great Red Spot. These models will help scientists understand whether the storm will eventually dissipate, and if so, whether a new vortex could form in its place, continuing the cycle observed over the centuries. The study of the Great Red Spot not only deepens our knowledge of Jupiter, but also provides insight into the behavior of large-scale vortices on other gas giants and even exoplanets. This new perspective highlights the importance of continuous observations and advanced modeling in unlocking the mysteries of our universe. Despite the vast differences between Jupiter and Earth, the dynamics of their atmospheres and oceans reveal surprising similarities. Recent research by physical oceanographer Leah Siegelman has shown that Jupiter's gas cyclones mirror the behavior of oceanic structures on Earth, offering new insights into the underlying mechanisms that govern these powerful systems. Jupiter's atmosphere, often described as an ocean of gas, exhibits cyclonic activity driven by convection, similar to storms on Earth. Convection is the process by which heat is transferred through fluid motion, and it plays an important role in both terrestrial and Jupiter weather systems. On Earth, convection occurs in both the atmosphere and oceans, creating storm fronts and ocean currents. A study by Siegelman, who analyzed data from NASA's Juno spacecraft, has identified filaments, wispy tendrils between Jupiter's vortices that behave similarly to fronts in Earth's oceans and atmosphere. These fronts, characterized by boundaries between masses of different densities, are crucial to the generation of strong winds and currents. On Earth, these density differences are usually due to variations in temperature and salinity, whereas on Jupiter they arise from temperature differences in the gaseous layers. By calculating the horizontal and vertical wind speeds of these filaments from infrared images, Siegelman's team confirmed that they contribute significantly to the energy dynamics of Jupiter's cyclones. These filaments help transfer thermal energy from the planet's interior to its upper atmosphere, which accounts for a significant portion of the cyclone's total kinetic energy and vertical heat transport. The presence of convection and fronts on both Earth and Jupiter suggests that these physical mechanisms are fundamental to turbulent fluid bodies throughout the universe. This finding implies that similar processes may exist on other planets with atmospheres or fluid layers, expanding our understanding of planetary science. The comparison of Jupiter's gas cyclones with Earth's oceanic structures provides a basis for the study of other celestial bodies. The ability to draw parallels between such different environments emphasizes the universality of certain physical principles, regardless of specific conditions. The advances in our understanding of Jupiter provided by the JWST and Juno discoveries not only expand our knowledge of the planet, but also set new standards for what can be achieved with advanced space telescopes and probes. High-resolution images and detailed data have revealed previously unseen structures and dynamics in Jupiter's atmosphere. These discoveries pave the way for future missions and exploration. Planned missions such as the European Space Agency's Jupiter Icy Moons Explorer will delve deeper into the Jupiter system, focusing on its moons, Ganymede, Callisto, and Europa. The purpose of these missions is to explore the potential habitability of these moons and further unravel the mysteries of Jupiter's atmosphere. Future space telescopes and probes will have more advanced sensors, enhanced data processing capabilities, and more sophisticated observational techniques that will enable even more detailed and comprehensive studies of distant planets and their atmospheres. By continuing to study the features of this gas giant and its similarities to our home planet, scientists will be able to better predict and model the behavior of the atmospheres of other planets, which, of course, will expand our knowledge of the cosmos and subsequently help in the search for habitable worlds. The journey is just beginning, so stay tuned as we continue to bring you the latest news and discoveries.
Today we'll delve deeper into the study of a phenomenon that is both violent and vital in the grand cosmic plan: the collision of planets. The cataclysms in which planets collide and merge are not just spectacular shows of cosmic fireworks. They are the architects of worlds, the creators of moons, and perhaps the creators of life itself. It is here, amidst the chaos of colliding worlds, that we find the solution to our planet's past and the mysteries of other solar systems. Our story begins about 4.5 billion years ago, with the colossal impact that gave birth to the Earth and its faithful companion, the Moon. Imagine two similar planets in the same orbit, pulled together in a cosmic embrace. This grand collision not only formed the Earth-Moon system, but also set a precedent for understanding the formation of planets in the universe. Recent astronomical observations thousands of light years away have recorded a similar but much more dramatic event. Two giant planets like Neptune collided at astonishing speeds. This collision was so powerful that it caused the light of their own star to be attenuated by a staggering 95%. Such observations make new adjustments to our understanding of cosmic events and indicate that planet collisions may be far more common than previously thought. From the birth of satellites to the mysteries of planet formation, today we'll witness the power of gravitational entrapment, unravel the history of our Earth and Moon, and look into the future of space exploration. Across the vastness of the universe, the birth of satellites is a tale of cosmic creativity. Satellites, or moons as we often call them, are born in many different ways, each telling a unique story of celestial mechanics and cosmic chance. One of the main ways in which satellite formation occurs is within the circumplanetary disk. This disk, composed of gas, dust, and debris, orbits around young planets like a miniature solar system. Over time, the material in this disk coalesces, giving birth to moons. The classic example is Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto. These moons form from the same disk that surround Jupiter when it was young, a process mirrored in miniature throughout our solar system. Another intriguing challenge is gravitational entrapment. This event occurs when a wandering celestial body, attracted by a planet's gravity, becomes trapped in its orbit. Neptune's moon Triton is a prime example of this. Astronomers believe that Triton, with its retrograde orbit, was captured by Neptune's gravity, and now the interplanetary vagabond is locked in endless tandem with its host planet. Finally, we explore the third, a violent but creative process resulting from the collision of giant planets. This scenario resembles a celestial race for survival, where the consequences of such colossal collisions can lead to the formation of moons. The origin story of our own moon is believed by many scientists to be the result of such a cataclysm. About 4.5 billion years ago, a Mars-sized body called Theia collided with the young Earth. The debris from this massive collision eventually coalesced to form the Moon, our permanent satellite. Each of these processes, formation in the near-planetary disk, gravitational entrapment, and the consequences of planet collisions, provide evidence for the dynamic and often tumultuous history of planet formation. Let's take a closer look at the thrilling spectacle of gravitational entrapment, the very process when a celestial wanderer drifting in space is captured by the gravitational pull of a planet, changing its fate forever. One of the most intriguing examples of this cosmic phenomenon is Neptune's largest moon, Triton. Unlike most moons in our solar system, Triton orbits Neptune in a retrograde direction, a clear sign of its dramatic past as a captured object. This unusual moon, with its icy surface and thin atmosphere, was likely a free-floating object in the Kuiper Belt before Neptune's gravity drew it into orbit. The Kuiper Belt is the region of the solar system beyond the orbit of Neptune. Although the Kuiper Belt is similar to the asteroid belt, it's about 20 times wider and 10 times more massive than the latter. The secrets of Triton's capture are not limited to its orbit. The event had a profound effect on both Triton and Neptune itself. The capture resulted in enormous tidal forces that altered Triton's internal structure and may have given rise to its geologic activity. In addition, it may have altered Neptune's orbit and axis of rotation. Capturing Triton is not only the story of the Moon, but also a window into the composition and evolution of celestial bodies in the outer solar system. By studying Triton, scientists can gain insight into the composition and characteristics of other Kuiper Belt objects. Its icy surface, with its nitrogen geysers and thin atmosphere, provides insight into conditions in this distant region of our system. The implications of Triton's capture extend to our understanding of planetary systems beyond our own. Such events can dramatically change the dynamics of a planet's moons and rings. This shapes our understanding of how satellite systems evolve and influences the search for similar phenomena in exoplanetary systems. Now let's move closer. As we've already mentioned, the Earth holds the secret of a turbulent and pivotal past, a secret it shares with its closest celestial partner, the Moon. The story of their birth is a story of cataclysm and creation, which determined the fate of both bodies as a result of a monumental event, the collision of planets. According to the giant impact hypothesis, about 4.5 billion years ago, a Mars-sized body called Theia collided with the young Earth. This colossal impact was not just an impact, but a catastrophe whose energy was enough to melt and vaporize both Theia and much of Earth. After this cosmic cataclysm, a disk of debris consisting of parts of Theia and Earth revolved around the molten planet. Over time, these fragments fused together under the force of gravity, giving birth to our Moon. The Earth, too, was forever changed. Its composition, axis, and orbit were altered by this collision. The evidence supporting this hypothesis lies not only in theoretical models, but also in tangible evidence. Samples of lunar rocks brought back by the Apollo mission are strikingly similar in composition to Earth's mantle, suggesting a common origin. In addition, computer modeling of this event accurately matches the current orbital dynamics of the Earth-Moon system. This theory has profound implications for understanding the history of the Earth itself. The impact probably played a crucial role in shaping the planet's geology and probably even its ability to harbor life. By stripping the Earth of some of its primordial atmosphere and altering its rotation, the impact may have laid the groundwork for the unique conditions that support life as we know it. Thus, when we look at the Moon, we are looking not just at a satellite of the Earth, but at a part of our planet's past, a celestial body born out of one of the most dramatic events, at least to us, in the history of our solar system. Among the accounts of the formation and evolution of our cosmic neighbor are other, often overlooked consequences of planetary collisions. These events not only shape the planets and their moons, but also leave behind characteristics and phenomena that further define the character of these celestial bodies. One such consequence is the formation of planetary rings. These beautiful and delicate structures that often adorn gas giants such as Saturn may be the result of collisions. These rings, although not formed directly from a single massive collision, are believed to be the remnants of smaller and more numerous events, from tiny ice particles to large chunks of rock orbiting Saturn. These bodies create the iconic appearance that we see today. Such rings are not unique to Saturn. They are a common consequence of collisions in planetary systems. Another intriguing result is the tilt of the planet. Uranus, with its peculiar axis of rotation, is a prime example. Astronomers suggest that a massive collision with an Earth-sized object in the distant past may have flipped the planet on its side, resulting in its extreme axial tilt of about 98 degrees. This tilt accounts for the planet's incredibly contrasting seasons and unusual magnetic field. Coming closer to home, Mars presents another intriguing case study. The Borealis Basin, a huge impact crater that occupies most of Mars' northern hemisphere, is thought to be the result of a colossal impact. The red planet also has a smooth, flat northern hemisphere, in stark contrast to the heavily cratered southern hemisphere. The dichotomy suggests that a powerful impact occurred in Mars' past, altering its surface and possibly also affecting its internal dynamics and subsequently the planet's climate and atmosphere. Even Venus, our sister planet, bears traces of a history of collisions. Its dense atmosphere, composed mostly of carbon dioxide with thick sulfuric acid clouds, raises questions about its past. Some theories suggest that comet impacts may have contributed to the dense atmosphere by delivering volatile compounds. These events may have created the greenhouse effect on Venus that led to the current inhospitable conditions. Each of these examples once again convinces us that even on such giant scales, collisions are far from rare. They continue to shape the physical characteristics, atmospheres, and even climate of planets, leaving an indelible legacy in their evolution. In the relentless pursuit of understanding the universe, astronomers have quite recently captured an amazing event: the potential collision of two giant planets. This unusual observation not only strikes our imagination, but also provides insight into the dynamics of planet formation and the evolution of stellar systems. Late last year, astronomers investigated observations made in 2021, an unusual phenomenon around the young star ASASSN-21QJ. This star, located about 1,850 light-years away, showed all the signs of such a grand event. The evidence? Significant infrared brightening and complex optical eclipse indicate a colossal planetary collision. The infrared enhancement of the star, corresponding to a blackbody temperature of 1,000 Kelvin and lasting about 2.5 years, was superimposed on a wavelength-dependent optical eclipse lasting about 600 days. These observations led researchers to hypothesize the collision of two exoplanets, each with masses ranging from a few to tens of Earth masses, located at a distance of 2 to 16 astronomical units from the star itself. Such a collision is a spectacle of cosmic proportions. Imagine two planets, presumably similar to Neptune, being attracted to each other by gravity and colliding at high speeds. The consequences? A debris cloud that attenuates 95% of the star's light, and an incredibly hot, glowing remnant visible in infrared light. The significance of this event goes far beyond its awe-inspiring visual impact. It provides a glimpse into the rare processes that form young solar systems. These giant collisions, predicted by theories of planet formation, play a crucial role in determining the architecture of planetary systems. The study of ASA SSN-21QJ is a testament to the importance of continuous astronomical monitoring. Such observations allow us to record these fleeting but informative events, shedding light on the dynamics of planet collisions and their role in the formation of solar systems. Events occurring during the early and turbulent stages of stellar system evolution play a key role in shaping the characteristics of planets and moons. At the stage of the birth of a star system, space is a crowded, chaotic place. Planets, planetesimals, and debris are in constant motion, often colliding and merging. These collisions can lead to the formation of larger planetary bodies, changing their orbits, composition, and even atmospheres. Take our Earth, for example. Its collision with Theia not only led to the formation of the Moon, but also contributed to the tilt and speed of the Earth's rotation. This impact may have played a crucial role in the formation of Earth's stable climate, which eventually became the basis for life and our existence. The recent observation of the star system ASA SSN-21QJ emphasizes the significance of these events. This colossal collision provided a huge debris cloud. Following this discovery, it becomes more apparent that such events, while dramatic, are not rare anomalies, and at the same time form an integral part of the evolutionary narrative of stellar systems. Planetary collisions can have a variety of consequences. They can strip a planet of its atmosphere or promote its development, affect its magnetic field, and even determine its potential habitability. The moons from these collisions carry the legacy of their parent planets, providing clues about the history and evolution of the systems. Collisions also play a role in the redistribution of materials within the solar system. Elements formed at the heart of stars disperse and recombine, contributing to the diverse compositions of planets and moons. This cosmic recycling is fundamental to understanding the diversity of worlds we observe in our galaxy. We've already moved into a new era in astronomy, and the future of research and discovery in planetary collisions holds great potential. Continued advances in technology and ambitious space missions have the potential to revolutionize our understanding of cosmic events. Current and future research depends heavily on advanced observational technologies. Ground-based telescopes are becoming increasingly powerful and can detect even faint traces of distant collisions. Space telescopes, such as the James Webb Space Telescope, offer unprecedented views of the universe, providing deeper insights into the mysteries of planet formation and destruction. Future missions specifically designed to study exoplanets will further deepen our understanding. The goal of these missions is to obtain direct images of exoplanets, analyze their atmospheres, and even possibly detect evidence of past collisions. The data obtained will provide a better understanding of how planets form and evolve. Along with advances in observations, computational modeling is also undergoing a revolution. Supercomputers are now able to model complex planetary collisions with greater accuracy, helping us to predict and understand the outcomes of these events. These models, supported by real observational data, will play a crucial role in testing and refining our theories. The study of planetary collisions is a global challenge. Collaborative projects and international partnerships play an important role in pooling resources and expertise. Such collaborations not only advance our knowledge, but also inspire future generations of astronomers and scientists. In the grand narrative of the cosmos, planet collisions are far more than just spectacular events. They are the sculptors of worlds, the creator of moons, and shape the very characteristics that make each system, each planet, and you and I so unique.
Our universe hides a mystery that's long captivated the human mind. a question that bridges the gap between the known and the unknown, the simple and the complex. Here on Earth, life thrives in a continuous movement of order and chaos. Every form of life is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammals. But what if the complexity of life, the very essence of our existence, could be explained not only through the lens of biology, but also through a mathematical framework? This is the territory of assembly theory, a groundbreaking concept that transcends traditional science. It's a journey into a world where math and biology converge to reveal the hidden architecture of life. Imagine a universe in which the secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and are waiting to be decoded, where the line between living and non-living is blurred, giving birth to new possibilities and new understanding. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. And maybe we can even get closer to answering the ultimate question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been the language of the universe, a tool for deciphering the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life? At its core, assembly theory offers a simple but profound idea. The complexity of life can be measured and understood through a mathematical prism. Think of life as a jigsaw puzzle, where each piece represents a molecular building block. Assembly theory seeks to show how these pieces come together step by step to form the complex structures that define living organisms. Each step in this assembly process represents a leap of complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index. The assembly index, the cornerstone of this theory, measures the number of steps required to build a biological structure. It's a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit into this? This standard model theory of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from the complexities of biology. However, assembly theory bridges this gap. In the field of assembly theory, the standard model lays the foundation for understanding forces and interactions. It's a bridge between the microscopic world of quarks and leptons and the macroscopic world of living things. Another important element of the theory is the concept of studying dynamical systems, phase space. This is a mathematical concept used to describe all possible states of a system. In the context of assembly theory, phase space allows us to map the path of the assembly of life. From a single point representing the simplest form of life, phase space expands, branching out into almost infinite possibilities. Each pathway representing a different route that life can take. In this limitless mathematical landscape, the paths of evolution and its complexities unfold. This mathematical framework gives us a new perspective on the complexity of life. It's not just about the particles and forces described by the standard model, but how these elements combine and interact over time to create the diverse pattern of life we see around us. This is where the chaos of random molecular interactions gives way to the order of living structures. So let's ask ourselves this question: are the complexities of life simply the product of chance, or is there a deeper cause? Let us consider two sharply contrasting concepts: complexity and entropy. Entropy, a measure of disorder and randomness, seems to be at odds with the complexity we observe in life. How do these opposing forces coexist in the natural world? It's here that assembly theory offers a revolutionary perspective. So, central to assembly theory is the assembly index, a revolutionary tool designed to measure the complexity of life. Think of it as a cosmic ruler, measuring the steps required to assemble a biological structure from its simplest components. Imagine a single molecule as the starting point on this scale. As you move up the scale, each step represents a more complex assembly, from molecules to cells and beyond. The higher the index, the greater the complexity, and the less likely it is that the structure could have arisen by chance. Now let's delve into the interaction between entropy and complexity. Entropy, a concept rooted in thermodynamics, suggests that systems naturally tend toward disorder. However, life defies this tendency, evolving from simple origins to a variety of forms combined into the complex ordered structures we see today. How does assembly theory resolve this apparent contradiction? It suggests that life is inherently a process of overcoming entropy. Through the lens of the assembly index, we see the complexity of life is not a challenge to entropy, but a journey through it. Consider the early Earth, a primordial soup of simple molecules. Over millennia, driven by the laws of physics and chemistry, these molecules began to assemble into more complex structures. Each step along the way marked a victory over entropy, a step toward greater complexity in life. Rethinking evolution through assembly theory, we see it not as a mere biological process, but as a mathematical inevitability. The emergence and evolution of life became a story of increasing complexity, a story written in the language of mathematics. Let us now turn to a very trivial question, but one that shines in a new light. Are we alone? The search for extraterrestrial life has captivated our imagination for centuries. Now, thanks to assembly theory, we have a new tool in this cosmic quest. Assembly theory offers a unique approach to detecting alien life. It's not about scanning the sky for radio signals or analyzing light spectra for the presence of oxygen. Instead, it's about understanding the complexity of molecules and structures that may indicate life. Imagine scanning the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of the samples in search of patterns that indicate the presence of life. The higher assembly index, the more likely it is that these molecules are the result of life rather than random processes. However, the road to discovering alien life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know. Life on Earth. What if it doesn't meet our biochemical standards? Another problem is the vastness of space. The universe is vast, and our ability to explore it is limited by current technology. Even with the most sophisticated telescopes and probes, we can only analyze a tiny fraction of the cosmos. Moreover, assembly theory, while powerful, is still in its infancy. It's a new approach, and its application to the search for extraterrestrial life is uncharted territory. There are questions about its applicability and accuracy in different environments, especially those that are very different from terrestrial environments. Despite these problems, the potential of assembly theory in the search for alien life is enormous. It could redefine our understanding of life in the universe, opening new doors in astrobiology. So assembly theory offers a new way of looking at life, not just as a biological phenomenon, but as an emergent property of cosmic complexity. Imagine the early days of our planet, a world in motion, a crucible for the chemistry of life. Here in this chaotic environment, simple molecules began the journey of assembly, a process governed by the laws of physics and chemistry, but leading to something much deeper. Life, according to assembly theory, emerges when these molecular structures reach a level of complexity that allows them to store and reproduce information. This is where chemical memory, a crucial step in the evolution of life, comes into play. Chemical memory is the ability of certain molecular structures to retain structure. In other words, we can say this is the blueprint for life. In the world of assembly theory, this is where reproducibility becomes key. The ability to reproduce these patterns, to pass them on from generation to generation, is what drives the evolution of life. From the simplest RNA molecules in the primordial soup to the vast diversity of life we see today, each step in this evolutionary journey has been a step up the assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not just a story of increasing complexity. It's also a story of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the depths of the ocean to the fringes of space. In the realm of scientific discovery, every new theory is scrutinized and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, now stands at a crossroads, being questioned by critical voices such as Dr. Hector Zennel. The critique presented by Zennel raises fundamental questions about the future evolution of assembly theory. Covering an impressive 18,000 words, the article will require time and thought, taking approximately 1 to 2 hours of dedicated reading. This is not a cursory look at the topic, but a deep dive into the heart of the scientific debate. For those who are interested, we leave a link in the description to both articles, the study and the counter-arguments to it. Looking to the future, the role of assembly theory in scientific research remains uncertain. Will it be able to adapt and overcome these challenges, or will it remain a footnote in the history of science? Despite the disagreements, one thing is clear. The debates surrounding assembly theory have initiated a conversation about the nature of scientific discovery. They emphasize the need for transparency, rigor, and humility in pursuing knowledge. In the end, the impact of assembly theory on future research may not lie in its specific claims, but in the lessons it teaches us about the scientific process. As we explore the mysteries of life and the universe, such theories will come and go. But the quest for understanding, the quest to unlock the mysteries of our existence, will always remain at the center of the interest of scientific research. For years now, there's been a concept that defies the very laws of physics as we know them. A dream that has spawned countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could potentially allow us to travel vast distances in space faster than light itself. Imagine a journey where time and space constraints yield to the power of human ingenuity, where the farthest corners of the universe suddenly become accessible. This isn't just science fiction. It's a puzzle that scientists have been piecing together for decades, ever since physicist Miguel Alcubierre proposed a theoretical model in 1994. Alcubierre's model, a bold combination of imagination and Einstein's theories, offers a way to bend the fabric of space-time itself. But what lies behind this bold idea? Is it a mere flight of fancy? Or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and breakthroughs surrounding warp drive. From the mysterious nature of negative energy to the tangled horizon problem. So let's dive into the depths of one of the most intriguing scientific quests of our time. The quest for the warp engine. Science or fiction? In the heart of Mexico City, amidst the hustle and bustle of city life, a young mind was fascinated by the mysteries of the cosmos. We're talking about Miguel Alcubierre. Born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and led him to the prestigious University of Wales, where he delved deeply into the fields of general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a breakthrough in world perception that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's break down the Alcubierre drive. Imagine a spaceship that does not move through space in the usual sense, but sits in a space-time bubble. This bubble, or deformation bubble, is the key to the Alcubierre concept. According to Einstein's general theory of relativity, massive objects distort the fabric of space-time. Alcubierre hypothesized that if we could manipulate space-time in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing the bubble forward. Behind it, space expands, pushing it from behind. Inside this bubble, the spaceship remains stationary, but the bubble itself moves, allowing the ship to move faster than light without violating the laws of physics. This idea doesn't involve moving the spaceship at high speed. Rather, it's about moving space around it. It's like putting a surfboard, a spaceship, on a wave warp bubble and letting the ocean, space-time, carry it. However, the Alcubierre model is not simply a manipulation of space. It requires exotic matter with a negative energy density to stabilize the warp bubble. This exotic matter is one of the many theoretical obstacles scientists face as they try to turn the Alcubierre drive from a fascinating theory into reality. Delving deeper into the practical aspects of the Alcubierre drive, we're faced with huge challenges that stand between theory and reality. The first of these is the scale of energy and mass requirements. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably huge amount, far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. An outstanding achievement was when physicist Chris Vanderbroek proposed modifications to the shape of the warp bubble. These adjustments dramatically reduced the energy requirement to about the mass of 3 suns. Still a colossal amount, but a significant step down from the original estimates. The second major obstacle is the need for exotic matter and negative energy. In the Alcubierre model, this exotic matter is crucial to stabilizing the warp bubble and making it function as intended. Negative energy is a peculiar and controversial concept. It's a concept in physics that can distort the very fabric of space-time. It's not just the absence of energy, but an actual physical quantity with negative characteristics. In the context of Alcubierre drive, negative energy will counteract the effects of normal positive energy, creating the conditions necessary for the existence and stability of the warp bubble. Negative energy, in the context of Alcubierre drive, is indeed a complex and somewhat elusive concept in physics, and it's important to distinguish it from the more familiar concepts of gravitational potential energy. In classical physics, the concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, like a planet, is considered negative energy because it takes work to move the object from the source of gravity to a point where this energy would be zero, for example, to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, the negative energy required for the Alcubierre drive is different. In this context, negative energy refers to a hypothetical form of energy whose energy density is less than zero. It's not just an accounting tool or a way of describing potential energy in a gravitational field, but rather a real physical substance or field with exotic properties, such as repulsive gravitational effects. This type of negative energy is not something we observe or well understand in the context of known physics. However, the existence of negative energy and, by extension, exotic matter remains a topic of intense debate and speculation in physics. Although phenomena such as the Casimir effect suggest the possibility of the existence of negative energy under certain conditions, harnessing it on the scale required for warp drive is a challenge. These challenges, the enormous energy requirements, and the need for exotic matter, underscore the monumental task of transforming Alcubierre drive from a theoretical model to a practical reality. They represent not just technological obstacles, but fundamental questions about the nature of the universe and our ability to manipulate its basic forces. As we move forward into the world of warp drive technology, we face another obstacle known as the horizon issue. This issue is at the heart of the Alcubierre drive design and poses serious problems for its practical application. In astrophysics, the horizon is often referred to as the boundary beyond which events cannot affect an outside observer. The most famous example is the event horizon of a black hole, the point of no return. Beyond this horizon, the gravitational attraction is so strong that nothing, not even light, can leave it. Similarly, in Alcubierre drive, the horizon is the boundary of a warp bubble. Inside this bubble, the spaceship is cut off from the rest of the universe, just as the interior of a black hole is isolated from the outside world by its event horizon. The horizon problem arises from the unique structure of the warp bubble itself. In the Alcubierre model, the spacecraft is located in a region of the space-time plane surrounded by a warp bubble that compresses space at the front and expands it at the back. This manipulation of space-time allows travel at speeds faster than the speed of light, but with a critical limitation. It isolates the spacecraft from the rest of the universe. Imagine being inside this warp bubble, the very mechanism that allows you to travel vast distances in space also prevents you from controlling the ship or interacting with the outside world. Communication signals, navigation commands, and even visual observations are all prevented by the bubble's boundary. Passengers and crew will not be able to control the spacecraft, correct its course, or even stop the journey once it's begun. The implications of the horizon problem are profound. It implies that a spacecraft driven by warp would essentially be traveling on a one-way, uncontrolled journey. This raises practical questions about using such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with celestial objects, or adjust our flight path to meet unforeseen circumstances? Moreover, this problem implies the need for a pre-established infrastructure, similar to an interstellar highway, with mechanisms to create and control the warp bubble from the outside. Such a requirement adds another layer of complexity to the already difficult task of realizing warp drive technology. While the horizon problem represents a significant engineering challenge, it is important to recognize that it doesn't invalidate the fundamental scientific validity of the concept. Theoretically, the principles underlying the warp drive remain unchanged and plausible within the framework of the general theory of relativity. As we delve deeper into the complexities of Alcubierre drive, we encounter another major problem, the radiation problem. This problem is twofold. It involves both the accumulation of radiation at the front of the deformation bubble and the potential effects of Hawking radiation within the bubble itself. First, let us consider the radiation accumulating at the front of the warp bubble. As the bubble moves through space at a speed faster than the speed of light, it inevitably encounters interstellar particles and cosmic radiation. These particles and radiation, unable to bypass the warp bubble, accumulate near its front end. Such accumulation poses a significant risk. When the warp bubble slows or stops, the collected radiation and particles will be released in a burst of energy. The intensity of this release could be catastrophic, not only endangering the spacecraft and its passengers, but potentially damaging any nearby objects at the destination. Moving inside the warp bubble, we encounter the second aspect of the radiation problem, Hawking radiation. This theoretical radiation predicted by Stephen Hawking, arises from the effects of quantum mechanics near the edges of black holes. In the context of Alcubierre drive, the intense warping of space-time around the edge of the bubble could create conditions similar to those at the event horizon of a black hole, potentially generating Hawking radiation. This radiation could have harmful effects on passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are profound. Not only do they pose serious engineering and safety challenges, but they also raise questions about the feasibility of long-duration travel using Alcubierre drive. Ensuring passenger safety and spacecraft integrity in the face of these radiation hazards is a critical area requiring further research and innovative solutions. It is a challenge that requires ingenuity and a deeper understanding of the interplay between quantum mechanics, the theory of relativity, and the harsh reality of space travel. When we turn our eyes to the current state of research in warp drive technology, we find ourselves in the thick of scientific research. Recent years have seen a flurry of theoretical papers and articles that break new ground in this field. One notable development has come from the work of physicists who've been revisiting the energy requirements of the Alcubierre drive. Based on earlier advances that significantly reduce the estimated energy requirements, recent papers have proposed various methods to further optimize the geometry of the warp bubble. These improvements are aimed at making the energy requirements even more feasible, approaching the realm of possibility. Significant contributions to the field have been made by researchers such as Harold White, who was instrumental in the experimental work on the feasibility of deformation bubbles and space-time manipulation at the NASA Eagle Works laboratories. Another area of active research is exploring alternative theories that could circumvent some of the limitations of the Alcubierre drive. For example, some physicists are exploring the possibility of using solitons, solitary waves that retain their shape while traveling at a constant speed, as a basis for creating stable strain bubbles without the need for negative energy. There's also growing interest in the role of quantum mechanics in warp drive physics. Researchers are delving into the quantum aspects of space-time and how they might affect warp drive mechanics. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the warp bubble. Recent theoretical advances also include the study of the effects of warp drive technology on causality and the fabric of space-time. These studies are critical in addressing potential paradoxes and time travel scenarios, ensuring that the concept remains grounded in physical laws as we know them. Little by little, the dream of warp drive technology is moving ever closer from the pages of science fiction into the realm of scientific possibilities, driven by the tireless efforts of researchers around the world. As we ponder the future of warp drive technology, we find ourselves at a crossroad of assumptions and possibilities. The realization of warp drives, a concept once confined to the realm of science fiction, depends on several key developments and breakthroughs. First of all, the theoretical problems associated with warp drive technology need to be addressed. This includes finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. Advances in areas such as quantum mechanics, exotic matter, and energy manipulation are critical to turning these theoretical possibilities into practical reality. Beyond the scientific and technical obstacles, the advent of warp drive technology brings with it many ethical and practical considerations. The ability to travel vast distances in space at unprecedented speeds would revolutionize space exploration, opening new horizons for humanity. However, with great power comes great responsibility. The ethical implications of such technology must be carefully considered. This includes the potential impact on space ecosystems, the responsibility to explore and possibly interact with extraterrestrial life, and equal access to this technology among nations and peoples. In practice, warp drive technology could lead to new methods of resource utilization, new ways of conducting scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space, from one of exploration to one of habitation and utilization. For now, we look forward to a future in which stars are not just points of light in the night sky, but destinations within our reach. This future promises uncharted territories and unprecedented exploration, beckoning us to continue our quest for knowledge and discovery.